Hello and welcome to Sleepy Science. Tonight we'll loosen the knot around certainty and drift across 30 quiet thresholds. You'll feel how a rule can soften when watched closely, how a pattern can be more real than a thing, and how silence can carry signals if you know where to listen. We'll let a mirror make time. Hesitate, invite motion to slow until it becomes a thought, and watch order arise from noise like a tide shaping sand. We'll weigh emptiness and find it gently heavy, touch a field and learn that matter is mostly rhythm, and see a single turn of phase redirect a river of outcomes. We'll follow a beam that calms its own jitters, hold a grain of light until it counts itself, and meet shadows that reveal what brightness hides. We'll step into spaces stitched by rotation and angle, share nows that don't quite agree, yet still hold hands, and notice how forgetting warms the world by a whisper. We'll listen for waves that carry no charge, yet move intent, steer interactions with almost nothing, and read the weather of the vacuum as if it were a sky. We'll watch randomness line up like dancers when given a gentle cue, feel edges that protect motion from bumps, and see distance shrink when too far things learn a common story. We'll let crystals sing, magnets draw paths without wires, and cooled atoms settle into a hush where possibility breathes. We'll borrow a bird's compass, a leaf's calm arithmetic, and a clock's shy admission that it keeps more than one time. We'll hold maps that admit they're smaller than their lands, walk to the center from anywhere, and wonder whether code precedes the play. If this kind of unhurried curiosity helps you rest, tuck yourself in, loosen your focus, breathe once, and let's begin. PT-Symmetric and non-Hermitian phases. Imagine tuning a system until gain and loss are not enemies but dance partners, one side gently feeding energy while the other sips it away, so perfectly balanced that motion neither explodes nor dies, and then nudging the balance by a hair and watching reality switch scripts. That is your doorway into PT-Symmetric and more generally non-Hermitian phases, where openness to the environment isn't a nuisance to be hidden, but a lever you can pull to reveal new kinds of order. In plain terms, you study systems that leak or absorb energy and ask whether symmetry, specifically the combination of parity and time reversal, can keep their observable behavior real and stable, at least up to a critical point. You don't need the heavy algebra to feel the idea. Picture two identical oscillators, or two optical waveguides sitting side by side, coupled so energy shuttles between them, and now give a faint push to one and a matching break to the other. If the push and break are balanced, the pair acts strangely ordinary, supporting steady oscillations with real frequencies, even though energy is flowing in and out. But if you twist the knob just past a certain threshold, the system crosses an invisible ridge called an exceptional point, and the two oscillation patterns that used to be distinct suddenly merge in identity. Their frequencies become equal and then peel off into complex twins. One mode grows, the other decays, and the very shapes of the modes coalesce. At that singular border, eigenvalues and eigenvectors meet and fuse, making the system hypersensitive and, under the right choreography, unidirectional in how it treats waves. Shine light from one side and it passes, shine from the other and it reflects or dies. A kind of one-way invisibility that's been realized in photonic lattices, where the material quietly eats light in just the right pattern. What makes this captivating for you is that the openness you usually try to eliminate, loss, gain, leakage, is being engineered as a resource. So the lab stops pretending every device is isolated, and instead writes the environment into the Hamiltonian's effective rules. Now PT symmetry isn't magic. Push the gain loss too far and you lose the real spectra. But in the safe side of the phase diagram, you discover paradoxes like loss-induced transparency where adding more loss in the right channel opens a window for transmission because the coupled partner borrows exactly what it needs, or lasers that share a cavity with their own coherent absorber twin, making thresholds tunable and modes selectable with unusual finesse. When you encircle an exceptional point by slowly sweeping control parameters, something deeply geometric happens. The system doesn't return to its original state after one loop. The two modes exchange identities, and only after a second loop do you come back home, leaving behind a measurable phase that isn't about distance traveled but about the topology of the energy landscape, like walking around a mountain pass that is actually a branch point where two sheets of a Riemann surface-like structure connect. This topology shows up in curious chiral behavior. Encircle the point clockwise and energy ends up in one mode. Go counterclockwise and it lands in the other, giving you asymmetric mode switching that can act as a built-in decision gate. People get excited about sensing here because tiny perturbations near an exceptional point can produce outsized changes. The splitting of resonances scales non-linearly. So in principle, a faint whisper in the environment becomes audible in the spectrum. Yet there is a sober footnote you should keep. The same openness that gives strong response also brings extra noise and broadened lines. So while the raw sensitivity looks spectacular, the actual precision you can guarantee under realistic fluctuations can be less dramatic. That debate, response versus ultimate metrological advantage, is still ongoing, and it's healthy, because it keeps you honest about what instruments can really deliver. On the hardware side, the playground is broad and concrete. Integrated photonic chips pattern stripes of gain and loss with nanometer control. Microwave resonators and electronic circuits simulate the same mathematics with resistors, amplifiers, and couplers. Acoustic metamaterials do it with cleverly damped and driven channels, so sound hears the one-way rules. And even mechanical setups with paired rotors or pendulums have shown the exceptional point physics with tabletop clarity. If you prefer a tangible picture, think of two metronomes coupled by a springy plank. With no gain or loss, they trade energy back and forth. Add a gentle push to one and a matching damper to the other, and you're in the PT-Symmetric phase. Still musical, still steady, until you cross the threshold and hear one metronome dominate while the other fades. The duet becoming a solo backed by a hush. This is not just a curiosity because practical devices crave directionality and control. Isolators that let signals pass only one way. Low-threshold lasers that pick a single clean mode without fussy mirrors. Switches that select channels by how you loop through parameters rather than how hard you drive them. And wave-based circuits that tolerate imperfections by shaping the environment instead of pretending it's absent. The broader non-Hermitian world goes beyond strict PT symmetry too, mapping out exceptional lines and rings in parameter space, showing how disorder or non-reciprocal couplings can reshape bands and steer energy to edges. But your takeaway for this chapter is focused and testable. By treating loss and gain as design ingredients, you open a second axis of control. Phase transitions not only in space or temperature, but in how a system exchanges energy with its surroundings. Practically, you learn to diagnose which side of the exceptional point you are on by measuring line shapes and mode profiles, to exploit adiabatic loops that are adiabatic only in the effective sense, to perform one-way state transfers, and to respect noise, because sensitivity without a noise budget is theatre, not metrology. Philosophically, there's a useful challenge for you as a listener. Reality is rarely closed, yet much of your intuition is trained on closed-box models, so PT-Symmetric and non-Hermitian phases invite you to think, like a gardener rather than a watchmaker, cultivate the surrounding conditions to coax the behavior you want instead of machining. Internal parts forever finer, and when you finish this segment, you should be able to explain to someone else, calmly and clearly, that exceptional points are not just weird math, but tangible crossroads where modes merge, symmetry breaks and directionality emerges, and that by learning to stand near those crossroads without stumbling, you gain a new kind of control over waves, whether they are light, sound, or the quiet oscillations of a mechanical beam. Floquet engineering, driving new physics into being. What if the surest way to discover new rules is not to change the stuff you're made of, but to tap a steady rhythm on it until it learns a different dance? Because that is the quiet secret of Floquet engineering. By driving a system with a periodic push, you don't just shake it, you rewrite the effective laws it follows. And you, listening now, can learn to treat time itself as a tool. Start with an image you can feel. Hold a child's swing and give it gentle, well-timed nudges, and you see how the cadence matters more than brute force. But then picture the opposite trick. A broom balanced on your palm that would fall if left alone, yet stays upright when you vibrate your hand just right. Because fast, regular motion can carve a new kind of stability where none existed. And that intuition scales all the way to quantum materials. Atoms in a crystal illuminated by a pulsing field, an array of cold atoms in an optical lattice that's shaken back and forth, or electrons in a two-dimensional sheet guided by a strobing laser. Each case uses a repeating beat to sculpt an effective landscape that didn't exist before. In practice, you look at the system not continuously, but strobe by strobe, comparing it to itself every interval of the drive and asking, what single, time-independent rule would mimic what one full beat just did? That rule is the effective description you can actually use to predict behavior, and it can defy your static intuition. Tunneling between sites can be suppressed to near zero even though the pathway is open, or it can even change sign, flipping whether waves prefer to spread or to huddle, a trick that lets you paint new band structures onto an otherwise ordinary lattice. In cold atom labs, people literally shake the lattice to switch on interactions that mimic magnetic fields where none exist. So neutral atoms swirl as if they felt Lorentz forces, making vortex patterns and edge currents you normally only expect from charged particles. And in photonic chips, researchers arrange waveguides in rings and modulate how light hops between them in time, generating unidirectional channels that carry light along the boundary, immune to small defects. A moving walkway written in time rather than in space. The reason this works is deeply simple. A periodic drive slices time into repeated chapters, and the full story over one chapter can be summarized by a compact instruction you apply again and again. The same way you might compress a long set of dance steps into 1, 2, turn. And this compression, this effective rule, can contain synthetic forces and geometric twists that aren't available in the undriven world. Under the right rhythm, electrons in graphene can be coaxed into topological behavior, acquiring protected edge motion even if the static material doesn't support it. And waves in photonic lattices can be routed around obstacles with graceful immunity to backscattering because the time pattern, not the material chemistry, guarantees the route. Yet the enticing power of driving always carries a shadow. If you pump too hard or too slowly, energy seeps into the many small motions of the system, and it heats like a pan left on the stove, washing out the delicate structure you just created, which is why the craft here is partly about speed. Fast enough that the system responds to the average pattern more than to the wiggles, but not so fast that your instruments and couplings can't keep up, and partly about cleverness. You can design sequences that cancel unwanted absorption, or work in regimes where the energy spread stalls for long, pre-thermal stretches, giving you clean, long-lived behavior even though, in principle, endless driving would eventually smear everything. Concrete examples help. In one family of experiments, the shaking is tuned so that atoms refuse to hop. Coherent destruction of tunneling, making a dynamic insulator out of a conductor without changing the lattice itself. In another, the drive is crafted to imprint a pattern of phases as particles loop around tiny plaquettes. So the gas behaves as if a strong magnetic field threads the sample, birthing swirling states and robust edges you can image directly. And in periodically driven spin systems, a different surprise appears. Patterns that repeat every second, third or fourth beat rather than every beat. A time crystal-like order where the response locks onto a rhythm that is a clean fraction of the drive, not because of broken equipment, but because interactions let the many bodies coordinate, sustaining a subharmonic tick that resists small imperfections. If you step back, the educational lesson is liberating. Material properties are not destiny, because temporal design can act like a new dimension of fabrication. Don't only sculpt where atoms sit, or what they're made of. Sculpt when and how you urge them, and you gain access to effective magnets without magnets, band gaps without chemistry, and pathways for light and sound that exist because you keep time. This reframes how you think about devices. A sensor can be made more selective by pulsing the world it samples, amplifying responses that match the beat and silencing those that don't. A quantum simulator can be tuned to explore exotic phases by programming a sequence of kicks that emulate forces no static table could host. Even everyday mechanical systems can be stabilized by vibration, in the way a microwave can levitate a fragile resonance into balance. Of course, there are limits you need to respect. Imperfections in timing smear the intended effect. Noise in the drive can seed unwanted heating. And real systems have many routes to absorb energy you didn't plan for. But the field has learned to tame those risks with tailored waveforms, pauses and echoes inserted into the sequence, and architectures that isolate the few degrees of freedom you care about. The philosophical payoff is worth your attention. Most of your intuition about control comes from shaping space, thicknesses, distances, barriers. Yet here you're invited to shape time instead, to use periodicity as a pencil that redraws what motion is allowed. So as you leave this chapter, you should be able to explain to a curious friend that Floquet engineering is not a buzzword for shaking things. It is a disciplined way to craft new effective laws by choosing a rhythm. You would tell them what to look for. Stroboscopic stability where none existed. Transport that survives defects because of a topological pattern built from timing. Insulators born from cancelled hops. Vortices conjured in neutral gases. And repeating responses that split the clock itself into steady fractions. And you would also know the honest cautions. Heating is the ever-present adversary. Lifetimes are finite, and the success of a drive depends on matching human-made rhythms to nature's internal tempos. If you can hold both truths, the creative freedom of temporal design and the practical boundaries set by dissipation, you will leave not with hype, but with a tool. The understanding that by learning to keep the right beat, you can drive new physics into being without inventing new matter. And that is a quiet, empowering thought to carry into whatever you explore next. Shortcuts to Adiabaticity. Fast without friction. Picture sliding a brimming glass across a table so quickly that not a single ripple forms on the surface. No slosh, no spill, just quiet arrival. And you have the feeling of shortcuts to Adiabaticity. The art of changing a system fast while leaving it as calm as if you had taken all the time in the world. In the slow ideal called adiabatic evolution, a system guided gently from one set of conditions to another stays in its instantaneous preferred state without spilling probability into unwanted motions. But slowness is a luxury you rarely have in the lab or in technology, so researchers learned to design precise, finite time pathways, pulse shapes, trap motions, and auxiliary fields that cancel the jostling that speed would otherwise cause, letting you go fast without friction. The central idea is not to brute force your way through, but to choreograph change so the system experiences a sequence it recognizes as smooth even when the clock runs quickly. And there are two broad flavors worth putting into your mental toolbox. Transitionless tracking, where you add a carefully tailored helper term that steers the system to follow the path it would have taken slowly. And inverse engineering, where you decide first how you want the state to behave in time, its size, its phase, its position, and then solve backwards for the control knob that makes that movie real. You can feel this without equations by imagining a trapped cloud of ultra-cold atoms held in a bowl-shaped potential. If you suddenly widen the bowl, the cloud normally sloshes, ringing like jelly in a jar. But a shortcut protocol prescribes a specific way to open the bowl. Accelerate, pause, decelerate in a pattern tuned to the natural timescales, so that the cloud ends up stationary in the new, wider home, as if you had stretched it infinitely slowly. Experiments have done exactly this in atom chips and optical traps, achieving frictionless expansion and compression that prepare delicate states on demand. And the same philosophy shuttles single ions rapidly between zones in a microfabricated trap without heating their motion, enabling faster logic in quantum information hardware. In mechanical language, you are suppressing diabatic excitations, the unwanted energy that appears because parameters change too fast, by destructively interfering the pathways that would otherwise dump population into excited modes. A cancellation accomplished by shaping the time dependence of the controls with surgical care. In one line of work known as transitionless driving, a helper field is built so that the evolving state always points along the moving target, preventing the sideways slip that speed induces, while in inverse engineered protocols, Families of smooth functions are chosen that satisfy boundary conditions like start in the ground state, end in the ground state, zero velocity at both ends. And then the required trap frequency or control curve is derived, giving you a recipe book of ramps that look deceptively simple, yet work reliably across platforms. This is not just a curiosity for cold atom fans. Similar ideas accelerate magnetic resonance sequences, so you can flip nuclear spins uniformly in samples with varying conditions. They speed up adiabatic passage in superconducting qubits for clean state preparation and population transfer, and they allow optomechanical resonators to be cooled and reconfigured quickly without exciting spurious motion that would spoil sensitive measurements. Most alluring, perhaps, is what these shortcuts do for thermodynamics under a microscope. A tiny engine operating in cycles normally pays a penalty when you hurry. Extra heat, extra entropy. Yet with shortcut-shaped compression and expansion strokes, you can approach the clean, reversible ideal at finite power, a practical path to devices that do more useful work per second without sabotaging their own efficiency. Honesty matters here, so you should also learn the trade-offs and boundaries, because nothing comes from nothing. A helper field must be produced and controlled with finite bandwidth. Inverse-engineered ramps demand accurate timing, and real devices carry noise and constraints, maximum amplitudes, limited couplings that can turn a perfect calculation into a nearly perfect experiment. There is also an energy-time tension in nature that sets speed limits. You can quicken the path, but to keep the motion clean, you often need stronger controls or added channels. And if those inject too much noise, the advantage shrinks. Clever workarounds exist, approximating hard-to-build helper terms with local fields, using composite pulses that self-correct errors, and designing smooth S-curve profiles that avoid sharp jolts. So the field has become an engineer's playground of recipes you can actually implement, rather than a mathematician's museum of ideals. Crucially, shortcuts are conceptually different from tuning material properties or imposing external rhythms. You are not trying to create a new phase of matter or draft a synthetic force. You are shaping a path between two ordinary points in parameter space, so the traveler arrives rested. A principle that generalizes beautifully from quantum systems to classical ones, like moving a delicate payload on a crane with a motion profile that leaves the hook motionless at the end. If you like to test ideas in your head, try this exercise next time you move something fragile. Instead of pushing evenly, imagine the anchor points, start and finish, then plan a path with a gentle lift, a brief coast and a mirrored settle, and you will glimpse why the same logic calms a quantum cloud. The deeper lesson worth carrying is that slow equals safe is not a law, it is a habit, and habits can be redesigned when you understand the levers. By learning the natural timescales of your system, and by giving it the exact sequence it needs, you buy back time without paying in disorder, which is liberating whether you care about faster quantum gates, quieter sensors, or simply the elegance of a world where speed and serenity are not enemies. As you step out of this chapter, keep one question open in your mind. When you next face a process that seems to demand patience, is there a smarter path that respects the system's limits, yet arrives early? Because shortcuts to adiabaticity are not a loophole or a trick. They are a disciplined way to choreograph change, so that even hurried motion feels like rest. And once you see that, you can't help but scan the physical world for places where a better path, not a slower one, will set the glass down without a ripple. Optimal quantum control. Imagine whispering to a quantum system in precisely the right sequence of syllables so that, despite its jittery instincts and the noise of the room, it does exactly what you want at exactly the moment you want it to. This is the spirit of optimal quantum control, not a new law of physics, but a disciplined way to design the time-shaped pushes and pauses that steer fragile states through a forest of pitfalls toward a clear target. The practical problem is simple to state and hard to execute. You have a limited set of buttons: microwave bursts for a superconducting qubit, laser pulses for trapped ions or neutral atoms, magnetic gradients in a spin system, and a limited time before the environment blurs your memory. And your job is to craft a waveform that turns start here into arrive there with high fidelity, while honoring the realities of hardware like bandwidth limits, amplifier distortions, crosstalk between neighbors, and the messy fact that your model of the device is never perfect. Rather than guess a pulse and hope, you define a score that measures how well a candidate waveform achieves your goal. Prepare a state, execute a gate, transfer population, suppress leakage into levels you don't use, then let algorithms climb that score's landscape, adjusting thousands of tiny parameters to maximize success under constraints you set. A process that feels less like solving a static puzzle and more like training a musical phrase until it lands cleanly every time. In gradient-based methods such as grape, you compute how sensitive the final score is to each time slice of the pulse, and then nudge all slices in the best direction, iterating until improvements stall. While in methods that work in a limited basis, think crab as an example, you choose a handful of tones or shapes and optimize their weights, a strategy that trades absolute freedom for speed and robustness. When your model is trustworthy, these open-loop optimizations are extraordinarily powerful. Laboratories have used them to carve 2-qubit entangling gates that run faster than hand-tuned sequences while keeping error below thresholds needed for error correction, to build selective pulses that flip 1 qubit in a crowded chip without nudging its neighbors, and to move population along chains or across energy ladders with near-perfect yield even when the steps are uneven. But models are never perfect, and devices drift. So the modern craft blends design with feedback. You start from a theoretically optimized pulse and then close the loop, updating it based on what the system actually did, using data from experiments, simple observables, randomized benchmarking scores, or short tomographic snapshots to push the pulse toward reality. A calibration dance that can be automated so that the system learns its own best instructions in situ. This learning in the loop is not hype. It is how cutting-edge platforms cope with day-to-day changes in frequency, amplitude response, and background coupling. And it can be coupled with machine learning only when it brings genuine advantage. Pattern discovery in high-dimensional spaces, not mysticism, because the physics still sets the boundaries. You cannot demand a turn faster than your strongest field allows. You cannot draw corners sharper than your filters can pass. And you cannot both outrun and outlast decoherence without acknowledging the trade. Optimal control is powerful precisely because it makes those trade-offs explicit inside the objective you optimize. You can demand short duration and accept a bit more power, or impose a cap on amplitude and let the algorithm extend the gate by a few nanoseconds. Or penalize rapid jumps so the pulse is friendly to your amplifiers. And you can explicitly punish leakage into higher levels so that a 2-level approximation remains honest on multi-level hardware. Even details as earthy as cable dispersion and mixer imbalance can be folded into the design by measuring the system's transfer function and pre-distorting the pulse so that after the hardware's wrinkles, the qubit experiences the ideal shape at the chip. There is a deeper lesson that helps you build intuition. The control landscape, under broad conditions, is surprisingly smooth, with few true traps, meaning that if your constraints are reasonable, gradient climbing tends to find a high-scoring solution rather than getting stuck forever in a bad valley. And when practical constraints do create roughness, you can soften it by changing the parameterization, widening the basis functions, or adding gentle regularization so the algorithm explores shapes humans would not guess, but hardware can realize. Beyond single tasks, the field now designs families of pulses that are robust by construction. Waveforms that perform well across a range of detunings, temperature shifts, or amplitude errors, like a lock that tolerates a slightly bent key. So the day-to-day fluctuations that once demanded constant retuning become tolerable background rather than acute crises. In systems with several interacting elements, optimal control also acts like traffic management. It schedules who moves when and how strongly, so that constructive interference builds the operation you want, while destructive interference cancels the paths that would cause trouble. A viewpoint that scales to bus-mediated interactions in superconducting architectures, to Rydberg arrays where blockade effects and motion matter, and to photonic networks where phase and amplitude must be shaped together. Verifying success is as important as designing it. So labs lean on metrics that actually mean something for computation and sensing, randomized benchmarking to estimate average gate performance independent of state preparation quirks, interleaved protocols to isolate a single operation's error, leakage checks that monitor population outside the computational subspace, and stability tests that rerun the same sequence hours later to see if the calibration held. The honesty clause is non-negotiable. Sometimes the pulse that looks great in simulation fails because a neglected coupling matters, or because the chip overheats under a high power segment, or because the algorithm found a solution that works only at one temperature. And those failures are not a condemnation of the method, but a reminder to tighten the loop between model and measurement, to include the missing physics, or to add a robustness term that punishes razor-edge solutions. Perhaps the most empowering way to carry this knowledge forward is to reframe control not as micromanagement, but as storytelling. You are choosing a path that the system finds natural, a sequence of gentle invitations that line up with its internal timescales, so that by the final beat it has no reason to be anywhere but where you intended. And when that happens across thousands or millions of repetitions, the payoff is real. Quicker, cleaner gates that push a platform closer to fault-tolerant thresholds, spectroscopy and imaging pulses that pull out weak signals from a noisy background, and state transfers that deliver population on target without scars. If you leave this chapter with one practical memory, let it be this. Optimal quantum control turns vague hopes like make the error smaller into a concrete recipe. Define what smaller means. Include the limits you cannot cheat. Let an algorithm search the shapes you cannot guess. And then close the loop with the hardware until the pulse that exists on a screen becomes a tool you can run every day. Because in a field where fragility is a constant, the ability to teach a system, the exact song it will reliably sing is not a luxury. It is how you make progress. Reservoir engineering, taming noise into order. What if the most reliable way to keep a quantum system quiet is not to seal it off from the world, but to design the world it talks to? Because that is the daring promise of reservoir engineering. You reshape the environment so that noise stops being a vandal and becomes a sculptor, steadily carving the state you want and holding it there while ordinary disturbances are drained away. Start with a picture you can feel, a marble in a landscape of hills and valleys. Then imagine you're allowed to redesign the landscape itself. You lower one valley until it becomes the only comfortable resting place, and you tilt the slopes so every random shove sends the marble toward that destination. And that is exactly the logic here, except the marble is a fragile quantum state, and the landscape is the pattern of losses, pumps, and couplings that connect your device to its surroundings. The key move is to pick a target that will be the unique, dark resting point of the dynamics, and then arrange every interaction so that anything that isn't the target leaks energy or information to a sink, while the target quietly refuses to couple. Like a harmony that does not feed the echo. This is the philosophy behind dissipative state preparation. A mouthful that simply means use carefully chosen loss to make the right state inevitable. And it has gone from idea to hardware. In superconducting circuits, for example, engineers combine a microwave cavity with a tailored parametric drive so that pairs of photons are added and removed in a coordinated way, and the only states that survive this tug-of-war are the two partners of a cat-like superposition inside the cavity. A code in which information lives in a shape rather than a spot. Once set, the engineered loss constantly repairs small mistakes. If random events nudge the state, the environment's rules guide it back, not by command, but by design, giving you autonomous stabilization without the need to continuously measure and correct from the outside. A closely related trick glues two or more qubits into a steady entangled pair by letting them share a mode that preferentially drains any pattern that is not the desired correlation, so that the wrong joint states bleed away and the right one remains, turning what used to be a delicate one-time preparation into a maintained resource. This approach is broader than any single platform. Optical pumping in atomic physics is a classic early version, where cycles of light and decay trap population in a desired sublevel that doesn't absorb anymore, and modern variants push that intuition into many body settings. using carefully phased lasers and engineered loss channels to funnel cold atoms into phases that would be hard to reach by cooling alone. Another powerful lens is to think about the character of the environment rather than just its strength. Ordinary noise often scrambles both amplitude and phase, but a squeezed environment can be made to quiet one variable at the expense of its partner. And if you choose the quiet direction to align with the way you encode information, the bath itself becomes a guardian that constantly damps the damaging fluctuations while allowing harmless ones to breathe. Similarly, one-way waveguides and cascaded connections let you direct the flow of disturbances like plumbing, so that information can leave a sensitive element without unwanted echoes returning, giving you diodes for noise. If you build intuition through examples, picture a three-step recipe that shows up again and again. First, you specify the goal, perhaps a protected pair of states inside a resonator, or a particular entangled relation between two devices. Second, you add drives and couplings that make all roads lead downhill to that goal, often by arranging interference so that only the desired pattern is invisible to the drain. Third, you tune the rates. Too weak and disturbances win. Too strong, and you heat or blur the very structure you need, until the return-to-home flow outpaces the random wanderings. The most beautiful aspect is the honesty it forces, because you are using the environment rather than denying it. Every hidden imperfection shows up quickly, and that helps you discover which processes actually dominate your platform. The slow drifts, the sudden jumps, the subtle crosstalk, so the engineered bath doubles as a microscope of your own device. There are, of course, limits you need to understand if you want to separate promise from hype. Engineered loss cannot fix every error at once, so you choose which mistakes to make rare and which to allow. And when you stabilize a set of states, you often give up some degree of freedom. Phase might diffuse even as amplitudes are protected, or the very drain that cleans errors can, on rare occasions, kick the system across the narrow ridge between the two code words you care about. Measurement-based feedback remains a powerful alternative, and in practice, the field blends both. Use the bath to do the heavy lifting continuously, and then sprinkle in occasional measurements to catch rare events the bath misses. Verification matters just as much as construction, so teams don't settle for pretty cartoons. They map out return rates back to the target after a nudge. They look for signatures like interference patterns in phase space that would vanish if the state collapsed into something classical, and they leave the system to run for hours to see whether the autonomous repair really outpaces drift. What you should carry forward is a shift in mindset. Instead of treating the outside world as a villain to be exiled, treat it as a material you can sculpt, by shaping loss, by adding pumps that are phase-locked to your device, by routing emissions so that they cleanse instead of contaminate, and you gain a second axis of control that complements hardware improvements and clever pulse design. This reframing unlocks concrete devices, memories that quietly hold quantum information, because the bath fixes small scratches before they spread. Sensors that keep their working points centered because the environment constantly pulls them back onto the sweet spot. Amplifiers that boost signals mostly in one direction while dumping back action into a sink you don't care about. And multi-element processors, where entanglement is no longer an event, but a background condition the circuit maintains by itself. And the philosophical nudge is gentle but deep. You have been taught to equate openness with fragility, but life, biology, and many resilient machines thrive by exchanging energy and information with their surroundings in a controlled way. Reservoir engineering borrows that wisdom for the quantum scale, asking you to design the leaks rather than deny them, to make the world's randomness do housekeeping for you. Leaving this chapter, you should be able to describe to a friend how a system can be made to prefer one state, not by fiat, but by flow. How an environment can be tailored to continuously undo small errors without watching every move, and why the remaining challenges, rare jumps, imperfect alignment, finite lifetimes, are not deal breakers but design targets. Because once you understand that noise can be domesticated, you stop dreaming of isolation and start getting practical about order, quantum illumination, and stealth detection. Suppose you're trying to spot a whisper in a stadium full of applause. Most of what reaches your ears is not the voice you care about, but a roaring wash of noise, and the trick, surprisingly, is to send out a paired whisper and keep its twin in your pocket, because later you can ask, did anything come back that still hums like your twin? That is the heart of quantum illumination and its promise for stealth detection. A counterintuitive idea where you transmit a faint, carefully correlated signal toward a region that might hide a low reflectivity object. You store the partner at home as a clean reference, and when the return dribbles in, swamped by thermal background and scrambled by loss, you don't measure it in isolation. You compare it against the twin, searching for a telltale correlation that pure noise is unlikely to mimic. Crucially, the advantage is not about keeping fragile entanglement alive on the round trip. Real environments shred entanglement so fast that by the time the signal bounces back, any textbook quantum bond is usually gone. But about the fact that the way you generated the pair imprints a subtle pattern of correlations that survive as statistical hints, the kind you can tease out with a receiver designed to recognize them, reducing the chance you'll mistake noise for a target under the same energy budget that a classical transmitter would use. To feel the idea without equations, imagine sending tiny, random-seeming pulses of light or microwaves whose randomness is secretly matched to your stored twin, phase. Wobbles here line up with phase wobbles there, and think of your receiver as a lock that only clicks if the rusted key still shares enough scratches with the pristine key you kept. In regimes that are the bane of ordinary detection, dim reflections, bright environmental noise, this matched key test can yield a lower error rate than any classical scheme with the same average power, not by boosting raw signal-to-noise in a single shot, but by improving the reliability of the target present versus absent decision when you average over many shots. There are several practical ways to build such a receiver. You can feed the return and the stored twin into a device that effectively undoes the original pairing operation and converts right kind of correlation into an ordinary brightness you can count. Or you can upconvert the pair into a single higher frequency mode whose intensity becomes a direct proxy for how well they match. Or you can use a phase-sensitive amplifier that selectively boosts the common fluctuations you expect from a true echo. None of these require you to maintain delicate entanglement all the way. What matters is that the transmitter created a pattern classical light cannot perfectly mimic under the same constraints, and that your joint measurement is tuned to reward that pattern. The stealth angle makes this especially intriguing. Modern stealth objects aim to reflect as little as possible and to shape what they do reflect so that it blends into the noise, forcing a radar to blast harder or to integrate forever, both of which can give away your presence. Quantum illumination takes a different tack. Keep the outbound energy low and the outward signature modest, but wring more information from the faint returns by comparing them to a stored twin. So your detection range in ugly, hot backgrounds can edge forward without cranking the transmitter to obnoxious levels. Honesty matters here, so confront the limits with clear eyes. Storing the twin cleanly for the whole round trip is hard at radio and microwave frequencies. Maintaining phase stability between what leaves and what stays is an engineering grind, and the theoretical advantage can shrink if your hardware introduces losses or extra noise before the joint measurement happens. In airborne or space scenarios, you must also cope with motion, clutter, and the need for timing and frequency sweeps to estimate range and speed, which means integrating quantum illumination with pulse compression and Doppler processing rather than treating it like a laboratory curiosity. Even so, progress is tangible. Benchtop systems have shown how correlated microwave pairs can be generated with parametric devices, how receivers can convert correlation into countable energy, and how in the worst classical corner, weak reflectivity, bright noise, the quantum-flavored approach can reduce the probability of a false verdict under fixed power. A win that matters when present or absent is the only question that counts. Beyond spot the dot, the concept extends to classification. If different targets imprint slightly different fingerprints on the return, a joint measurement can help discriminate between them with fewer pulses. And in passive sensing, where you listen to a noisy scene without transmitting, tailored correlations might still help if you can seed part of the environment with a reference field and later compare, though that's a more speculative direction and must be weighed against practical constraints and ethics. What quantum illumination does not do is magic. It won't let you see through mountains. It doesn't guarantee a dramatic range jump in every scenario, and it doesn't invalidate the physics that makes stealth effective. It simply rebalances the trade by shifting effort from brute force power to smarter inference. The right way to carry this forward is to think like a systems engineer. Design sources that make bright, stable pairs without splashing excess noise into the band. Build memories that keep the reference honest long enough to matter, and craft receivers that do the joint test with minimal added noise. Then wrap all of that in real radar tasks, scanning, tracking, rejecting clutter, staying within regulations, so that any quantum advantage survives contact with the world. Philosophically, there's a useful challenge for you. You've been trained to think of noise as an enemy that washes information away, but here you learn that information can hide in relations, not just in isolated signals, and relations can be surprisingly persistent, like a melody you still recognize on a battered recording because the gaps and rises match what you remember. If you can learn to listen for that melody, to design transmitters and receivers that reward the right coincidences, you gain a quiet edge in the most unfriendly conditions, which is why the field keeps pushing past demonstrations to integrated prototypes. Leave this chapter with a practical sentence you could tell a skeptic. Quantum illumination won't make a weak echo loud, but it can make your decision about that echo more trustworthy when everything else is loud. And in a world that increasingly prizes low signature operation on both sides, hiders and finders alike, that extra bit of trust, earned honestly and measured against the same energy budget, is the difference between guessing in the dark and hearing a whisper with enough confidence to act. Ghost imaging with unused photons. Imagine taking a picture with a camera that never looks at the object. Your lens stares at blank space while, somewhere else, a different detector that can't form images at all simply counts how much light got through. And yet, after you compare the two streams of data, an image of the hidden thing quietly appears. This is the unsettling charm of ghost imaging with unused photons, a technique that teaches you to value relationships over direct contact. Because what matters isn't an individual photon's path, but the shared pattern that links two beams born together or shaped by the same randomness. Here's the simple workable idea. You split a light source into two arms, a probe beam that interacts with the object, and a reference beam that never goes near it. Then you detect the probe with a single pixel bucket sensor that records only total brightness, no spatial detail, while a separate camera measures the reference's brightness distribution across many tiny spots, capturing a map of speckles or structured patterns that were also present in the probe at the moment it touched the object. For each snapshot, you multiply the bucket reading, how much got through right now, by the reference's map, what pattern existed right now. And you do this again and again across a sequence of random or designed patterns. Average those products over time, and the object's silhouette blooms out of what looked like noise. Because regions of the reference that tended to be bright whenever the bucket reading was high must correspond to places where the probe often found a path through the object, while regions that tended to be bright when the bucket was low mark, where the object usually blocked the way. The philosophical jolt is immediate. The unused photons at the camera never touch the object, but their arrangement correlates with the outcomes of their twins that did. So your image is really a map of correlations, not a pile of direct reflections, which is why this method can work even when the probe arm is so faint or scrambled that a normal camera would fail, although ghost imaging made its name with pairs of photons generated. Together, down conversion in a crystal produces twins whose speckle patterns match shot by shot. The same logic can run with classical light too. You can create known patterns with a digital micromirror device, or use a moving diffuser that splashes fresh speckle for each exposure. And as long as you know the pattern in the reference arm, while the bucket measures total transmission in the object arm, the mathematics of averaging correlations does the rest. This isn't magic, and it doesn't smuggle information across space without interaction. The only reason the unused beam is informative is that both beams share a common origin or a common script, so their frames line up in time even if they travel different routes. But the practical consequences are quietly powerful. First, the probe can work at wavelengths where good cameras are scarce or expensive. Terahertz, mid-infrared, deep ultraviolet, and you can still build your image using a cheap visible camera in the reference arm because the pattern correlation lives in time rather than color, a neat trick when you want to sense water content in leaves or chemical signatures in a material that reveal themselves outside the visible spectrum. Second, the probe can be extraordinarily dim, even at levels safe for sensitive samples, yet still produce an image over many shots because the reference camera supplies the spatial information that the bucket lacked, and the averaging discards uncorrelated noise like a careful listener, ignoring crowd chatter and locking onto a friend's rhythm. Third, ghost imaging can be surprisingly tolerant to certain kinds of distortion, turbulent air, scattering fog, or imperfect optics, because the reference doesn't suffer those distortions, and the correlation process emphasizes whatever features genuinely track with the object rather than with environmental flicker. There's an even thriftier variant called computational ghost imaging, where you don't split the beam at all. You illuminate the object with a known sequence of patterns and record only the bucket signal, then reconstruct by correlating that single time series with the script of patterns you commanded, a method that trades a complicated camera for a smart light source and a bit of computation, and can shine in low-cost or eye-safe scenarios. Honesty is essential, so learn the limits alongside the luster. Ghost imaging rarely produces a good picture in one shot. Its strength comes from averaging many realizations so that true correlations stand above random coincidences. So acquisition times can be long if the object is dim or if you need fine detail. The resolution is tied to the scale of your patterns and the optics that generate them. And while clever algorithms can push beyond naive limits by favoring sparse or compressible scenes, there is no free lunch. You must encode enough distinct patterns to learn the structure you want. Alignment in time matters because the bucket and reference must be paired correctly for each exposure, and any drift in the source or the diffuser can blur the correlation. And while quantum sources can offer statistical advantages in the most unforgiving regimes, very low light and heavy background, those advantages shrink if your detectors or memories add loss and noise before the joint analysis. So real systems must be engineered as carefully as any radar or camera. Still, the technique opens doors that classical imaging usually shuts. You can form an image after the probe has been scrambled by a random mask as long as the reference records the corresponding pattern. You can mix and match wavelengths, shining long-wave radiation, onto the object, while recording high-resolution visible patterns in the reference to reconstruct shapes that visible light alone would never reveal. You can do standoff measurements with tiny average power because the information lives in how the whole sequence hangs together, not in how brightly a single pulse returns. And you can test ideas for imaging through partial occlusions or in situations where a high-quality camera cannot be placed near the object, like hazardous environments or sealed vessels with a single fiber acting as the bucket. Beyond the lab, the mindset is as valuable as the machinery. Ghost imaging trains you to think of information as something that lives in concert, not isolation, a harmony you can extract by comparing signals that share a history, even when each signal alone seems worthless. It asks you to design your illumination as if you were composing music, a sequence of notes that, when later cross-referenced with a simple loudness meter, reveals the shape of the stage, and it rewards patience, because clarity grows as you gather more pages of the score and let the average do its quiet work. If you carry one practical lesson away, let it be this. When direct images are impossible or impractical, you can still learn shape by measuring coincidence. Pair a simple, global sensor with a partner that knows the pattern and use correlation to sift signal from noise. And carry one philosophical question too. How much of what you think you must touch directly could be known by attending to relationships instead, by listening for echoes between two places rather than staring harder at one? Because ghost imaging, done honestly and without hype, shows that unused does not mean useless. It means waiting for the right companion. And sometimes the clearest picture is the one you assemble from the parts that never met your subject at all. Electromagnetically induced transparency. And slow light. What if you could politely ask an opaque cloud to step aside and then watch a pulse of light tiptoe through at walking speed? Sometimes, even pause and wait for your signal without changing what the cloud is made of, only how you talk to it. That is the quiet miracle of electromagnetically induced transparency and the slow light it unlocks. A phenomenon where a strong control beam teaches an ensemble of atoms to interfere with themselves so that a narrow window opens in the middle of an absorption line and, more subtly, the refractive index in that window gains a razor-steep slope that forces pulses to crawl. At heart, the mechanism is simple enough to picture. Imagine a three-level atom shaped like a letter with two long-lived ground-like states sharing a common excited state up top, and shine two different colors. One strong control tuned to one leg, and one weak probe tuned to the other. So that there are two quantum pathways for the atom to absorb and re-emit the probe. With the right frequencies and phases, those pathways cancel the very act of absorbing the probe, producing a dark superposition of the two lower levels that refuses to climb to the excited state, which means the gas that was once a wall to the probe becomes, within a narrow slice of color, nearly transparent. But transparency is only half the story you should care about, because the real power for shaping pulses comes from dispersion, the way the material delays different parts of the probe's spectrum, and under EIT that delay changes dramatically over an extremely small bandwidth. The refractive index barely changes in magnitude, yet its frequency dependence becomes so steep that the group velocity of a pulse, the speed of its envelope, can be reduced by thousands or millions of times compared to its usual sprint. So a pulse that would normally traverse a centimeter in a tenth of a nanosecond can take microseconds instead, lingering long enough that your electronics and timing can catch their breath. If you flip your viewpoint from light in a medium to light entangled with motion of the atoms, you meet a useful hybrid called the dark state polariton, a gentle combination of a probe photon and a coherence between the two long-lived states. And this picture explains the most enchanting trick. Turn the control beam down while the pulse is inside and the polariton sheds its photonic part, coming to rest as a spin wave pattern in the atoms, a stored memory of the light's shape and phase. Later, turn the control back up, and the stored pattern redresses itself with light, releasing a near-faithful copy of the original pulse, which is why EIT has become a central route to quantum memories for single photons and entangled states in the visible and near-infrared, memories that trade speed for gentle handling and can be chained together to build repeaters and synchronizers for quantum networks. The effect is not restricted to one pristine setting. It has been observed in ultra-cold gases where Doppler blur is small, in warm vapor cells that are cheap and robust, in solid-state ensembles like rare earth ions in crystals, where coherence can last astonishingly long at low temperatures, and even in microresonators and photonic structures, where the cascade of modes and couplings mimics the same interference, though the vocabulary shifts. When you watch an EIT trace on a scope for the first time, the magic looks almost too clean, an absorption peak split by a control into a sharp transparency notch, and a delayed, reshaped pulse emerging much later than you expect. Yet the craft behind that calm curve is practical and learnable. The control's power sets the width of the window and the depth of transparency. The detuning balances loss against dispersion, and small magnetic fields that split the ground. States can help isolate a single pathway from lookalikes that would pollute the darkness. It is important to keep the claims honest, so let's separate wonder from myth. Slow light here means reduced group velocity, not that individual photons plod through the medium like marbles in syrup. Their energy is repeatedly converted into atomic coherence and back again as the polariton advances. And if you make the window too narrow, you will simply distort and absorb parts of the pulse whose frequencies fall outside the sweet spot. There is also a bandwidth delay trade-off that engineers live with. The narrower you make the window to increase delay, the smaller the range of pulse shapes you can pass without distortion. which is why real systems speak of a bandwidth delay product that limits how many distinct temporal features you can store or slow at once. Decoherence is the ever-present adversary. Stray collisions, magnetic noise, residual motion in warm vapors, and imperfect optical pumping all erode the long-lived coherence that the dark state relies on. And in dense media, nonlinear processes like four-wave mixing can sneak in, amplifying unwanted light and adding noise that a quantum memory cannot tolerate. So careful shielding, buffer gases, anti-relaxation coatings, and control of beam geometry are part of the everyday toolkit. Still, when tamed, EIT gives you capabilities that are hard to match by other means. You can match a fast photonic network to a slower crystal processor by pausing photonic qubits on demand. You can enhance light-matter interactions by letting pulses linger where sensors or nonlinearities await, effectively giving the medium more time to listen. You can build devices that synchronize streams of single photons for interference experiments without throwing most of them away. And in metrology, you can exploit the steep dispersion to measure tiny frequency shifts as changes in delay, turning timing into a spectroscopic probe. There are thoughtful cousins to EIT worth knowing, so you can see the boundaries clearly. Autler splitting also produces a two-peak structure, but stems from strong dressing rather than destructive interference, leading to different conditions for transparency. Coherent population trapping shares the dark state idea, but is often used to lock atoms into a non-absorbing state for clocks rather than to sculpt dispersion. And fast light, where the group velocity becomes superluminal or even negative, can appear in related dispersive tricks. Yet it does not move information faster than light, and does not violate causality. The front edge of a signal still respects the universal speed limit, so these striking plots should be read as reframing the envelope's march, not rewriting relativity. To test your understanding, imagine designing a memory for a faint pulse carrying a delicate quantum state. You would choose a medium with long ground state coherence, align the control so its intensity profile matches the pulse's entry and exit, tune detunings to maximize transparency while keeping the dispersion steep enough to stop the pulse within your cell length. Measure and cancel unwanted magnetic gradients so that each slice of the spin wave shares the same rhythm, and verify storage by retrieving the pulse and checking its shape and correlations against the input. If that sounds like careful cooking rather than mysticism, you've learned the right lesson. EIT is not a slogan, but a recipe that turns absorption into a lever and timing into a handle. And perhaps the deeper reflection is this: most of your intuition about seeing depends on light rushing to you as fast as nature allows. Yet here you are invited to slow that rush, to treat speed as a design variable, and in doing so, to notice how much control hides in the places you thought were fixed. Absorption lines, refractive indices, the simple word transparent. When you walk away, carry this sentence you can offer to a curious friend. With the right control, light can pass through what used to block it. And while it passes, you can decide how quickly its shape moves, even pause it and store it as a whisper in the atoms, provided you respect the trade-offs that make the trick real. Because in a world where communication and computation hinge on timing, the ability to tell light not just where to go, but how fast to get there is a gentle, practical kind of power. Autler splitting. Imagine shining a strong, steady tone of light on an atom and watching its once simple resonance peel apart into a pair of crisp peaks, as if your flashlight had quietly turned a single note into a duet. This is the Autler effect, the most direct lesson in what it means for matter to be dressed by a field, where the atom and the driving wave stop being separate characters and become a coupled actor with new energy landmarks. To build intuition, start with a ladder of 3 levels: a lower state, a middle state, and a higher state that you probe with a weak beam, while a second, strong beam couples the lower and middle states hard enough to matter. In the absence of the strong drive, your probe sees one clean absorption line into the top level. But once the drive locks the lower pair into a rapid exchange, the probe no longer finds a single target. It sees 2 hybrid possibilities, 2 dressed combinations that share the job the top level used to do alone. And so, your spectrum splits into 2 peaks separated by an amount that scales with how vigorously you shake the system. Nothing needs to be mysterious here. The strong field continually mixes the states it addresses, creating new superpositions that are stable in the presence of that drive. And the weak probe is merely a reporter, mapping this mixed basis as two allowed transitions instead of one. Much like how a heavy pendulum coupled to a second pendulum no longer swings at its old frequency, but at two new ones, defined by their partnership. There is an elegant geometry, hiding in plain sight. Sweep the strength of the drive, or the detuning of the beams in those twin peaks trace out the same avoided crossing, curves you see in countless coupled systems, a bent X shape that announces, these modes talk to each other, and that curve becomes a ruler for the coupling itself, giving you a direct visual calibration of how strong your control really is. This is why experimentalists love Autler towns splitting as a diagnostic. It turns an invisible parameter, the dipole strength of a transition, the amplitude of a microwave tone on a chip, the overlap between states, into an obvious measurable distance between peaks, a yardstick you can read off a screen without fitting an elaborate model. The effect shows up across platforms, because all you need is a strong, coherent drive and a probe. In atomic vapors, you see the doublet bloom as you raise the control power. In trapped ions and neutral atoms, the splitting becomes a tuning fork for calibrating gate speeds. In circuit QED, the same physics appears when a qubit is driven strongly, and a weak readout tone maps how its transition dresses. And in quantum dots, the optical spectrum reveals the same fingerprints. A reminder that dressing is a general idea rather than a niche trick. It also clarifies a confusion you may have met when learning about transparency. A narrow window in an absorption profile can arise from two very different mechanisms: destructive interference that forbids absorption in the first place, or strong field dressing that simply moves the allowed transitions out of the way. And Autler towns belongs to the second camp. The practical difference matters because the conditions for the window and its sensitivity to parameters are distinct. Interference-based transparency can survive at lower control strengths, but is fragile to any process that ruins phase relations. While Autler towns splitting needs the drive to be strong enough to carve two distinct peaks, and once carved, those peaks follow the strength like loyal markers. If you want a tactile picture of the dressed state viewpoint, imagine the strong beam as a continuous handshake between two levels, so continuous that those levels stop existing as solitary roles and become two new shared roles. Call them in step and out of step. And your weak probe must now hire one of these partners to reach the top. This handshake leaves other signatures too. Drive the transition so strongly that the system's own light emission changes character, and you meet the famous trio of peaks known as the Mollo triplet, a close cousin of Autler towns that appears not in absorption but in fluorescence, reinforcing the lesson that strong driving reshapes how an atom absorbs and how it glows. Engineering-wise, Autler towns splitting is more than a curiosity because it acts as a knob you can turn to create selective pathways and to block others. By addressing a transition, you can displace it from where your environment is noisy. You can isolate one qubit from another by pulling their lines apart on demand. You can perform sideband selective operations by aligning one of the dressed branches with a desired motion, and you can read out states by arranging that only one dressed line overlaps your probe, making bright or dark responses conditional on the state you want to learn. Yet the honesty clause applies. Strong driving brings side effects like power broadening, heating, and spectral crowding when nearby transitions get dragged into the dance. So the art is to drive enough to split clearly while keeping the rest of the spectrum tidy. Mislabeling can also mislead. At modest powers, a tiny notch can look like a transparency, even though no true interference is at play. So careful scans of how the feature depends on control strength and detuning are essential to decide whether you're seeing interference or dressing. To demystify this for yourself or a colleague, outline a simple experiment in your mind. Prepare a 3-level system where one lower leg can be driven strongly. Sweep the frequency of a weak probe that climbs from the other lower state to the upper state. Record the transmitted or absorbed power as a function of probe frequency while you vary the control power. And watch the single resonance blossom into two peaks that separate as the control grows. plot the peak positions versus the control strength and confirm the smooth avoided crossing. Then check the peak widths to quantify broadening and stability. With those few steps, you've turned an abstract idea into an instrument you can use to calibrate couplings, measure transition dipoles, and verify that your control hardware delivers what its dials promise. The deeper lesson you should carry is that levels are not fixed shelves in a museum. They are living, context-sensitive features shaped by the fields you apply. And Autler Town's splitting is your first clean look at that living landscape, where a single tone of light sculpts new rungs on the ladder and a weak probe draws their outline. When you leave this chapter, keep one simple sentence ready for anyone who asks. Dressed states are the atom plus the drive acting as one system, and Autler Town's splitting is their signature in a spectrum, a practical, honest marker that you can see with your eyes and use with your hands to control and to measure. No mysticism required, only a strong handshake and a careful ear. Strong, ultra-strong, coupling in cavity and circuit, QED. Imagine locking a single quantum of matter and a single quantum of light in the same tiny room and turning up the interaction until you can no longer say which one is speaking. Only that a new, joint voice has appeared, and then keep turning the knob until even the quiet background of empty space joins the duet. That is the intuition behind strong and ultra-strong coupling in cavity and circuit QED, where an emitter trades energy with a well-defined electromagnetic mode so rapidly that the swap outruns losses, and then, in the ultra-strong limit, so intensely that processes you normally ignore come roaring into relevance, rewriting what light and matter even mean inside the device. In the familiar weak world, an excited atom drops a photon into the cavity and, before it can grab it back, noise and leakage spoil the exchange. But cross the threshold where the coherent handshake is faster than those leaks, and you enter strong coupling. Spectra show a clean vacuum. Rabi split, one resonance becomes two, because the true excitations are no longer one photon or one atom flip, but hybrid polaritons, shared quanta that are half field, half emitter. Watch how those two peaks move as you tune the atom or cavity, and you'll see the unmistakable avoided crossing of a genuine partnership. A ruler for the coupling strength that experimenters use to calibrate devices from optical microcavities and photonic crystal boxes to microwave resonators lithographed on a chip. Linger here and you can perform coherent operations. Swap an excitation back and forth like a heartbeat. Buffer a fragile state in the field while you prepare the next step. Or let two emitters talk through the shared mode to entangle at a distance. All because the interaction is not a perturbation, but the main act. Now push further, ultra-strong coupling, where the rate at which light and matter talk becomes a sizable fraction of the very frequencies that define them, and a quiet assumption breaks. The energy-conserving only story no longer holds. So terms that create or destroy a pair of excitations together, usually dismissed as too feeble to matter, start shifting levels and seeding correlations right into the ground state. You can feel what that means without math by imagining that the vacuum inside the cavity is no longer a perfect silence, but a correlated murmur between the field and the emitter, a bound cloud of virtual quanta dressing the lowest energy configuration. You cannot pull this cloud out directly without changing the system, but you can see its fingerprints. A shift of spectral lines, known historically from strong radio frequency driving, appears cleanly even with a steady field. Selection rules soften, letting transitions once forbidden gain small but measurable strength. And if you suddenly quench the coupling or modulate the boundary conditions fast enough, a portion of that virtual cloud can be converted into real photons. A cousin of dynamical Casimir tricks, where motion or rapid parameter changes mine energy from the drive into light. Platforms that make this regime practical are diverse and concrete. In circuit QED, galvanically linking a superconducting qubit to a high-impedance resonator, or engineering a flux qubit with a large dipole moment, creates normalized coupling ratios that would be fantasy for natural atoms, while losses stay low enough for clean spectroscopy. In the optical world, organic molecules packed into microcavities or plasmonic gaps can couple collectively so strongly that even at room temperature, you see wide Rabi splittings and modified chemistry pathways, although dephasing and inhomogeneous broadening add texture that must be modeled honestly. Two-dimensional materials and inter-subband transitions in semiconductor wells add new knobs, tunable densities, adjustable oscillator strengths, making it possible to scan across regimes without changing the cavity itself. What becomes possible once you live here is not vague. You can tailor emission spectra and lifetimes by shaping the hybrid character of the modes, routing energy along the branch that interacts less with a lossy environment. You can design gates in which a cavity is not merely a wire, but an active mediator that can be switched and detuned to control who talks to whom and when. You can attempt non-perturbative quantum simulations where the light-matter Hamiltonian itself, with all its counter-rotating features intact, is the physics you want to study rather than something to tame. And you can explore ground state properties where entanglement exists even without excitations in the usual sense. A conceptual nudge that forces you to separate what you can directly count from what shapes the energy landscape you measure. The caution list is as important as the promise. In ultra-strong coupling, simple rotating wave pictures fail, so intuition built on clean swaps and perfect number conservation gives way to dynamics where measurement backaction and non-Markovian memory play larger roles. In circuit hardware, higher levels of the qubit leak into play and need to be accounted for or suppressed by design, else your beautiful two-level cartoon bleeds probability into side channels. Thermal photons at microwave frequencies creep in unless you cool deeply and manage infrared leaks through every cable and connector. In organic and plasmonic systems, losses can be the price of strength. So strong in a spectral sense does not always mean coherent in a time domain sense. And you must decide whether your goal is to reshape optical properties for chemistry and energy transport, where line widths may be acceptable, or to execute reversible quantum logic, where they are not. Even the language demands care. Talk of superradiant phase transitions and macroscopic ground state fields must honor constraints from gauge consistency and realistic forms of coupling. Modern analyses show that some earlier predictions of dramatic ground state order vanish when you write the theory in a fully consistent way, but they also highlight where genuine, measurable ground state correlations persist, and how to reveal them with quenches and carefully shaped probes. For someone building devices, the practical playbook is straightforward and hard-won. Maximize the dipole that couples the emitter to the selected mode and the impedance that turns that dipole into a large field. Minimize unintended couplings to all other modes that only add dissipation. Characterize your cavity spectrum so you know which features are hybrid physics and which are simple multi-photon artifacts. And verify with both frequency sweeps and time domain experiments. When it works, the signature is unmistakable. Clean anti-crossings that refuse to close, split peaks that widen linearly with your control parameter, and dynamics faster than any single loss channel. And the payoff is real. More faithful interfaces between stationary qubits and flying photons, stronger nonlinearities per photon for detectors and switches, and platforms where the basic grammar of one quantum here, one quantum there, gives way to a richer syntax, in which the joint phrase is the fundamental object. If there is a single idea to carry out of this chapter, say it like this. In strong coupling, light and matter form shared quanta you can watch and use. In ultra-strong coupling, even the vacuum of that partnership is dressed, shifting behavior in ways you can measure and sometimes harvest. No mysticism, only the honest consequences of turning interaction from a whisper into a shout. And if you respect the engineering limits while embracing the non-perturbative rules, you can build machines where the line between field and emitter is not a boundary, but a design space. Ground state cooling in optomechanics. Imagine holding a tiny mirror, no larger than a grain of sand, on an invisible spring and asking it to be so still that its remaining motion is just the restless jitter nature gives even the calmest object. Nothing more, nothing less. That is the aim of ground state cooling in optomechanics, where you use light inside a cavity not simply to look at motion, but to slow it, reshape it, and finally quiet it until the average number of vibrational quanta is pushed below 1, meaning the resonator spends most of its time in the lowest rung of motion allowed by quantum mechanics. The doorway into this craft is a force that sounds gentle but acts with precision. Radiation pressure. The tiny push from photons ricocheting between mirrors. Place a mechanical element as part of a high-finesse cavity, so that when the element moves, it shifts the cavity's color slightly, and when the cavity fills with light, the circulating photons push back on the element, creating a feedback loop through the field. By choosing the color of your laser a little to the red of the cavity's preferred tone, you bias the scattering events so that photons preferentially steal energy from the motion, a process often described as anti-Stokes scattering, turning mechanical quanta into slightly bluer light that leaks away through the output mirror. This dynamical back action is not a marketing phrase, but a real, tunable friction that, in the right regime, beats the natural heating from the environment. The regime matters. If the cavity can distinguish a photon whose energy has shifted by one mechanical quantum, that is, if the cavity line width is narrower than the mechanical frequency, then each cooling event is spectrally selected, and you can drain motion efficiently without immediately re-exciting it. An approach called resolved sideband cooling that mirrors the logic of laser cooling in atomic physics, but works on a vibrating object you can see under a microscope. The lab recipe is deceptively simple to state and surprisingly hard to execute. Build a cavity with low loss and small moving mass so that the mechanical element strongly affects the optical resonance. Pick a mechanical mode with high quality factor so it doesn't leak energy too quickly back to the world. Cool the whole device to cryogenic temperatures so you start with fewer quanta to remove. And then tune the red detuned laser power just high enough that the cooling rate outpaces every source of heating without tipping the system into instability. Measure progress honestly by watching the noise spectrum of the mechanical motion. As cooling deepens, the peak around the mechanical frequency narrows and its area shrinks. And at the deepest levels, an asymmetry appears between the upshifted and downshifted light leaving the cavity because removing a quantum and adding a quantum no longer happen at equal rates. This asymmetry is a thermometer that works even when the motion is too small to assign a classical temperature. Alongside this passive method lives an equally important complementary route, measurement-based feedback cooling, where you detect the motion in real time, then push back with a tailored force using the same light or a separate actuator, choosing the phase so your force opposes velocity rather than position and therefore drains energy. This active approach does not rely on the cavity's spectral filtering and so can cool modes that evade sideband selection, but it inherits the honesty of any measurement. Your detector adds noise, your electronics add delay, and if either is too large, you make things worse. The quantum limit shows up in both strategies under different clothes. Back action, because the very act of probing motion with light jitters the force through photon arrival randomness, and as you turn up power to improve readout or speed cooling, this fluctuating force can reheat what you're trying to quiet. The engineering art is to choose a working point where imprecision noise and back action noise are balanced by the coherent cooling rate, a tug of war that sets the best achievable occupancy for a given device, laser, and environment. Progress, measured against these honest limits, is striking. Drumhead membranes clamped by nanostrings, photonic crystal beams with co-localized light and sound, microtoroids and crystalline disks that trap whispering gallery modes, and even levitated nanoparticles held in optical or electrical traps have been brought within a breath of, or into, their ground state, with phonon occupancies well below 1 confirmed by sideband thermometry. At that point, a different world opens. You can add a single quantum of motion on purpose with a faint pulse and watch it decay. You can squeeze one quadrature of motion below its 0-point value by tailoring the interaction so fluctuations are shifted from one variable to its partner. And you can entangle the resonator with a traveling pulse of light, enabling protocols where information carried by photons is temporarily parked in a mechanical memory and later retrieved. These capabilities are not parlor tricks, but tools for technology. force sensors that can detect zeptonewton pushes by quieting their own rumble, microwave to optical transducers that convert signals between superconducting circuits and fiber networks by using a mechanical mode as the middleman, and timing devices where the mechanical element stabilizes an optical frequency or vice versa. The practical pitfalls are concrete and solvable rather than mysterious. Absorption in the mirror coatings or the resonator itself can heat the device just where you shine the most light, turning the cooling beam into a tiny stove unless materials and wavelengths are chosen carefully. Clamping losses drain vibrational energy into the chip, unless the supports are engineered like acoustic filters. Two-level defects in amorphous materials soak up and release energy unpredictably, broadening lines. Laser phase noise masquerades as real motion if not filtered. And photothermal forces, an inadvertent push from tiny temperature gradients, can either help or hinder depending on delays in geometry, so they must be modeled and tamed. Teams address these by moving to crystalline films with low internal loss, by patterning phononic shields that reflect vibrational energy back into the mode, by choosing laser wavelengths far from absorption bands, by using balanced homodyne detection that rejects common mode noise, and by calibrating every meter and knob so quoted occupancies rest on verifiable references rather than optimistic fits. The frontier now includes more adventurous ideas, using squeezed light as the cooling field so that the back action it imposes is quieter in the damaging direction, shaping the cavity density of states. So cooling is enhanced only where you want it, and coupling multiple mechanical modes so that one mode acts as a refrigerator for another through engineered interactions, a mechanical analog of sympathetic cooling. Perhaps the most thought-provoking payoff is conceptual. When a chunk of matter made of trillions of atoms sits primarily in its lowest motional state, you gain a platform to test where quantum behavior gives way to the classical rules your intuition expects. Not with vague philosophy, but with concrete interference and decoherence experiments that probe how mass, geometry, and environment conspire to protect or destroy delicate superpositions. In the end, the lesson you can bring to someone curious is plain and powerful. By letting light and motion talk inside a carefully built cavity, and by choosing color, power, and geometry with care, you can drain nearly every last wobble from a tiny mechanical object until the only motion left is the quantum restlessness no force can remove. From that quiet starting line, you can measure more gently, store information more faithfully, and explore more deeply the boundary between the everyday and the quantum, not through slogans but through devices that hum with a steady engineered calm. Levitated nanospheres and macroscopic superpositions. Picture a dust mote held perfectly still in mid-air, not by a thread or a tiny arm, but by fields you can't see. And then imagine letting that mote float freely for a heartbeat, while you nudge its quantum phase just enough that, as it drifts, two distinct possibilities for its position blossom and later meet again to draw an interference pattern. You can only explain if a truly chunky object was in a superposition of places at once. That is the frontier of levitated nanospheres and macroscopic superpositions, where you trade the solidity of a mount for the purity of levitation. So the world has fewer ways to tug on your experiment, and you try to persuade not a single atom, but a billion of them bound together to behave with the same delicacy that textbooks reserve for electrons. The practical reason levitation matters is blunt. When a particle is glued to a substrate, vibrations, friction, and thermal creep spoil the game. But when it's held aloft, by the light of an optical tweezer, by the push-pull of electric fields in a pole trap, or by diamagnetic suspensions, the only handles remaining are the gas that slips by, the photons you use to see and steer it, and the particle's own thermal glow. With those handles under control, you can calm the center of mass motion until its residual jitter is mostly the unavoidable quantum restlessness. And then you have a platform that is light enough to be moved by single quanta and heavy enough to make any interference you observe feel like a challenge to common sense. How do you get there without drowning in detail you don't need? First, you isolate. Pump the chamber down so air doesn't buffet the particle. Pick materials and wavelengths so your trap doesn't heat it from the inside. Tame stray charges on its surface with ultraviolet flashes or gentle electron floods, and quiet technical noise in the fields that hold it. Second, you measure motion as gently and precisely as possible. Scattered light carries a record of position you can read with a split photodiode or interferometric detection, and you use that record to apply feedback, a force that opposes velocity and drains energy, or a parametric tweak that stiffens and softens the trap in step with the motion to squeeze the oscillation down. Sometimes you enlist an optical cavity to provide a spectral filter that favors cooling, scattering over heating, scattering. But levitated systems also shine because they can cool far with feedback alone and then be fully released. Something clamped resonators cannot do. Once the jitter shrinks and the particle sits nearly at the floor of its motional ladder, the dream of a macroscopic superposition becomes a sequence you can visualize. You briefly turn off the trap, so the wave function spreads like a soft cloud. You imprint a spatially structured phase with a standing wave grating pulse that makes certain locations pick up a different phase than their neighbors, and you let the free evolution continue so that those phase-tagged pieces of the wave function drift and later overlap, producing near-field interference fringes that a camera cannot see, but your detector can read out by how the final recaptured motion depends on the grating. Variants of this script use magnetic forces on tiny embedded spins, or optical double wells that split and recombine the center of mass motion without ever touching a surface, or pulsed electric fields that kick a charged bead into two paths with a timing accuracy a drummer would envy. The obstacles are concrete and honest. Residual gas molecules blur the phase by random hits, photons scattering from the very light that traps and measures you adds, momentum kicks that accumulate like sand in a bearing. Black-body photons absorbed and emitted by the warm interior of the sphere carry witch path information you can't erase, and small patch charges on nearby electrodes can whisper forces you didn't mean to apply. None of this is fantasy or hand-waving. You can estimate each rate and watch it change when you tweak pressure, temperature, wavelength, or geometry. And progress is measured in how each term is pushed down until a planned delocalization remains coherent over the time it takes to form fringes. Why push so hard? Because these experiments are some of the cleanest ways to test whether quantum theory needs help at larger scales. Objective collapse ideas predict that massive objects spontaneously lose coherence faster than atoms do, with rates that grow with size or mass distribution. So a clear interference pattern from a nanosphere after a long, clean free flight directly rules out chunks of that belief. Equally, there are proposals that gravity itself might act like a private environment that eats phase information, not by pulling but by entangling space and time with the object's position. And the only way to see the difference between mundane decoherence and a new rule is to build systems where mundane sources are quiet enough that any extra loss of visibility would stand out. To keep you grounded, here is what a real run could look like in your mind's eye. A silica sphere around 100 nanometers across sits in a softly focused 1064 nanometer tweezer at ultra-low pressure. Its motion read with heterodyne detection. Active feedback cools the three motional axes until the standard deviations are a tiny fraction of the trap size. The tweezer is then extinguished for a millisecond of freefall, while a short standing wave pulse engraves a phase grating across space. Then darkness again, while the matter wave fans out and self-images at a near-field revival time. Finally, the trap is turned back on to recapture whatever remains, and a scan of the grating timing or phase reveals a set of oscillations in recapture probability that line up with an interference model only if the particle's center of mass explored more than one classically distinct path. Run after run, you randomize any hidden biases, and you watch the contrast die if you deliberately add gas or raise the particle's temperature, and you watch it survive when you swap in better vacuum, cleaner materials, a colder environment, or a different grating that your classical simulation says should not help. Meanwhile, the same platform doubles as an exquisite force meter. The very sensitivity that makes superpositions fragile lets you read minuscule forces from patch potentials, short-range deviations from Newton's law, or tiny magnetic gradients, an applied payoff that keeps the engineering sharp. The frontier does not stop at tabletop scale. Microgravity flights and space proposals exist, because letting the wave function breathe for seconds rather than milliseconds demands long, quiet freefall that the lab can't provide without mirrors and tubes that would just reintroduce noise. And in that environment, delocalizations grow from submicron to many microns, where competing theories disagree more loudly. Throughout, the tone you should keep is cautious but hopeful. No one has unambiguously shown an interference fringe for a truly massive free-flying object, yet at the scale philosophers dream about. But every ingredient has moved from speculation to hardware, stable levitation, deep cooling, clean release, coherent phase imprinting, and recapture readouts with shot-to-shot reliability. The deeper lesson you can share without hype is simple and empowering. By taking away every mechanical contact and letting a tiny solid drift as if it were a single particle, you earn the right to ask whether the rules that make electrons wave also allow visible matter to wave. And by counting the clicks that remain after you remove every ordinary excuse for blur, you either watch a heavy object draw quantum fringes, or you discover where and how the world refuses. Both outcomes are knowledge. When you leave this chapter, hold one sentence ready. Levitated nanospheres turn isolation into a tool, letting you test whether superposition is a privilege of the small or a right of all matter. And the truth will not arrive by slogan, but by careful control of gas, light, heat, and time until a speck of glass behaves less like a bead and more like a whisper that can be in two places at once, and then meet itself again to prove it. Quantum acoustics, phonons as bus wires. What if the quietest way to link quantum devices is not with light racing down a line, but with sound gliding through a crystal? Slower, denser, exquisitely shapeable, so that vibrations themselves become the wires that carry information. That is the promise of quantum acoustics, and the idea of using phonons as bus wires, where you route single quanta of sound across a chip to connect qubits, memories, and sensors with a medium that couples naturally to matter, bends around corners with engineered ease, and lingers long enough to interact strongly without overwhelming power. Begin by resetting your intuition. At a few gigahertz, a photon's wavelength on chip is centimeters, but a phonon's in a solid is micrometers. So an acoustic cavity that would be impossibly large for microwaves becomes a neat structure carved in a thin film. And a waveguide that would struggle to confine light can channel sound through phononic band gaps like a river between tall, patterned levees. This size advantage meets a second gift: impedance. Because many quantum objects couple more directly to strain than to free space fields. So a carefully placed, interdigitated transducer can convert an electrical microwave tone into a surface acoustic wave whose strain pattern hugs the chip and whose energy density near the qubit is orders of magnitude higher than in a comparable electromagnetic mode, buying you stronger, cleaner interaction at the same drive level. In practice, you craft three ingredients: a source that can launch single or few phonon excitations on demand, a line or cavity that shepherds those excitations without scattering them into junk modes, and a receiver, another qubit, a mechanical memory, or a spin ensemble that can catch the phonon and use it. Sources often start electrically. A superconducting qubit encodes a bit of energy. A piezoelectric transducer turns that into a packet of surface acoustic wave with a shape set by chirped fingers and apodized apertures. And the packet slips into a phononic waveguide whose periodic holes or slots open a bandgap that bans leakage. So only your intended channel carries the sound. Along the way, you can insert filters and bends the way you would in photonics, but now the wavelengths are smaller, and the scattering can be suppressed by geometry more easily. So a tight 90-degree corner or a compact ring can live beside sensitive devices without acting like an antenna. Inside acoustic cavities, bulk resonators, thin film overtone devices, optomechanical crystal defects, quantum control becomes a game of timing. Ring up a standing wave with a tailored pulse, swap an excitation between the cavity and a qubit by parking them in resonance for a calibrated tick, or park the phonon in a dark mode whose strain avoids lossy boundaries so that it sits for milliseconds at millikelvin temperatures, long enough to serve as a genuine memory. Because sound is slow, delay lines a millimeter long can store signals for microseconds, so you can build on-chip buffers and interferometers where path differences that would require meters of coax happen in a postage stamp area, making Hong-Ou-Mandel-style interference and time bin protocols plausible with phonons if your sources are quiet and your detectors are honest. Hybrid connections widen the map. Strain couples directly to color centers like NVs in diamond and to rare earth ions in crystals. So the same acoustic bus that talks to a superconducting qubit can, via well-placed structures, write to or read from spin-based memories that hold coherence far longer than the qubit itself. Couple that to an optical cavity that feels the same breathing mode, and you have the scaffold for transduction. Microwave in, phonon across, photon out, an essential step toward linking cryogenic processors to room temperature fiber networks without showering the fridge with thermal light. None of this is free. The very slowness that gives you strong coupling also hands the environment more time to misbehave. So every phonon that grazes a rough edge, a grain boundary, or a patch of amorphous oxide risks scattering into a forest of unwanted modes. Thermal occupancy is a fierce adversary because at gigahertz frequencies a bath above a Kelvin still holds many phonons. So real devices work deep in dilution refrigerators and surround their waveguides with phononic shields. Periodic structures that open wide gaps so thermal vibrations cannot wander in. Piezoelectric layers bring their own blemishes. Two-level defects in sputtered films absorb and release energy erratically, turning perfect ringdowns into ragged tails unless materials and growth are chosen with care. Packaging matters more than pride would like to admit. One bad epoxy bead can leak acoustic energy or introduce a spurious mode that robs your cavity of quality, factor, and even the metal lines that route control signals can siphon energy unless laid out with an acoustic eye. The engineering responses are tangible and teachable. Swap amorphous for crystalline films where possible. Polish edges to the point that Rayleigh scattering is a footnote. Choose high-impedance resonators to boost strain per quantum at the qubit. And shape transducers so that their spectral skirts are clean, else bus wires become broadcast towers. Verification is as important as construction. You don't claim a single phonon channel because the schematic looks pretty. You measure swapped excitations between distant qubits mediated only by the acoustic line. You observe interference that vanishes when you deliberately scramble the phonon's phase. You check anti-bunching statistics of emitted sound, or more commonly today, you infer them via the qubit's response to time-separated emission attempts. When you see coherent revivals as a phonon bounces between mirrors, or a programmable delay that produces predictable entanglement phases across a small network, you stop wondering whether sound can carry quantum information and start deciding which protocols benefit most from it. The most compelling uses play to strengths: routing and buffering on chip without bulky components, strong interaction with matter at modest powers, and compatibility with materials already favored in superconducting and spin platforms. Sensing is another beneficiary. An acoustic mode confined in a phononic crystal cavity is an absurdly good accelerometer or force meter once quieted, and when it couples to a qubit, you gain both quantum-limited readout and the ability to squeeze or shape noise so that the variable you care about is watched more gently. Stay honest about limits. Phonons are not a universal solvent. Long-distance links still favor photons, and room temperature operation washes out most quantum structure. So the sweet spot is cryogenic, on-chip, and hybrid, where sound complements light and charge rather than replacing them. The philosophical shift is modest but deep. You are used to thinking of wires as passive metal that carry currents and of light as the fast courier for quantum states. But in carefully patterned solids, the lattice itself becomes a sculptable network whose tiny ripples are couriers just as capable, and in some contexts more willing, to whisper information from one quantum element to the next. If you leave with one sentence ready to share, let it be this: phonons make excellent quantum bus wires precisely because they are slow, dense and intimate with matter, traits that, when engineered with bandgaps, clean materials, and calibrated transducers, turn vibrations from a source of decoherence into a medium of control. So the next time you picture a quantum chip, don't only draw waveguides for light and traces for microwaves. Sketch the invisible roads of sound that knit the whole machine together. Polariton chemistry, editing reactions with light. Imagine walking into a laboratory where the recipe for a chemical reaction includes not only reagents, solvent, and temperature, but a mirror-lined box set to a very particular color. Close the box, tune the color until the molecular vibrations or electronic transitions feel it, and the reaction that used to crawl now runs, or the pathway that favored one product now leans toward another, as if you had redrawn the hills and valleys of the reaction landscape without swapping a single atom. That is the working intuition of polariton chemistry. When you place a reacting system inside an optical cavity and couple a molecular transition strongly enough to the confined electromagnetic mode, light and matter hybridize into polaritons, new quasi-particles whose energy and character are shared between photons and molecular excitations, and this shared identity can subtly edit kinetics and selectivity even when you never shine a bright laser or absorb a photon in the usual sense. The practical setup is startlingly down to earth. Two high reflectivity mirrors make a microcavity. A thin film or solution of molecules sits between them, and the spacing is adjusted so that one cavity mode resonates with a chosen transition. Often a bond's vibrational motion in the mid-infrared, sometimes an electronic transition in the visible. If the collective interaction of many molecules with that mode overcomes losses, the single absorption line splits into two polariton branches separated by a gap whose size scales with the square root of the number of coupled oscillators, a direct spectral sign that the vacuum field of the cavity is not a bystander. The polariton branches carry part photon, part molecular character, but an equally important cast of dark states sits between them. Combinations of molecular excitations that remain mostly matter-like and don't talk to light directly. Chemical consequences arise because the cavity reshapes the density of states and the way energy flows among these actors, changing how vibrational energy is exchanged with solvent, how a transition state is stabilized, or how populations drift toward one coordinate rather than another. In vibrational strong coupling, a bond like CO can be dressed by the cavity so that its vibrational energy doesn't leak into the bath as readily, or leaks along unusual channels, which experiments have associated with altered reaction rates, shifted isotope effects, or surprising selectivity in cases like deprotection reactions, solvolysis, and crystallization where one polymorph becomes favored over another. The most provocative point, and the one that draws both excitement and skepticism, is that some of these changes persist without pumping. The cavity's vacuum fluctuations and the coherent sharing of energy among many molecules can bias dynamics at room temperature, implying a background edit to the potential energy surface rather than ordinary photochemistry, which depends on absorbing real photons. To keep your understanding honest, separate claims into categories. There are robust demonstrations where coupling clearly shifts nucleation pathways, changes crystallite shapes or tips polymorph ratios in reproducible ways, pointing to modifications of early-stage aggregation and energy redistribution. There are kinetic studies where rate constants shift under coupling, sometimes dramatically, and careful controls, detuning the cavity off resonance, swapping mirrors for bare cells, keeping temperature and concentration fixed, help isolate the cavity as the active ingredient. And there are more contentious regimes where small apparatus differences or uncontrolled heating could masquerade as an effect, reminding you that the field is young and that meticulous baselines, blind procedures, and independent replications are the currency that converts surprise into confidence. Mechanistically, several pictures compete and may all be partly right depending on the system. One view emphasizes that polaritons alter the curvature along a bonded coordinate, effectively stiffening or softening motion so that barrier crossing skews. Another stresses kinetic funnels in a many-body landscape, where the dark state reservoir serves as a staging ground from which population can climb into polariton channels that dissipate differently, steering energy away from side reactions. A third points at solvent and friction. If coupling locks a mode into a more collective rhythm, the way it exchanges energy with its environment changes, like a choir that breathes together and therefore tires differently than soloists, which can show up as an apparent enthalpy entropy rebalancing in Arrhenius plots. Electronic strong coupling adds yet another layer. By hybridizing a bright electronic transition with the cavity, You reshape how excitons move and relax, sometimes suppressing quenching or enabling uphill transfer that would be improbable in the dark. With knock-on effects for photoredox catalysis and charge separation yields, it's tempting to oversell this as alchemy. So let's draw the lines clearly. Polariton chemistry does not let you violate thermodynamics or conjure brand new elements, and most reactions cannot be turned on or off like a lamp. What it does offer is a non-contact knob for tuning energy landscapes, a way to push on barrier heights, pre-equilibria, and dissipation pathways by choosing which internal motion the cavity couples to, how tightly it couples, and how the mirror geometry selects modes. That knob is collective by nature, because many molecules share the same field. Effects often scale with concentration and film thickness in ways that simple single-molecule pictures miss, and the dark states, though invisible to the cavity, are the bulk of the Hilbert space where chemistry really happens. So understanding how they communicate with polaritons is part of the design problem. On the engineering side, the recipe book is getting practical. Choose mirror separations and angles to tune the resonance. Use metals for broadband, but lossy cavities or dielectric stacks for narrow, low-loss ones. Pick plasmonic gaps to cram fields into nanometric volumes when you want very high local coupling, while managing the heat and losses that ride along. And always build detuned controls, identical, cells whose mode sits just off the target frequency, to separate true coupling. Effects from mundane issues like altered diffusion in thin films or thermal, gradients near reflective layers. Verification must go beyond pretty splitting. Correlate spectral signatures with kinetic measurements. Track isotope effects to test whether changes scale like you expect. And measure product distributions and crystallography, not just rates, because selectivity is where cavity control can shine. Application spaces are concrete, steering which crystal form a pharmaceutical prefers, biasing a catalytic cycle toward a cleaner branch, stabilizing or destabilizing intermediates that are useful in synthesis, and tuning energy transfer pathways in optoelectronic blends so that charges separate more efficiently before they find each other again. Philosophically, the field invites a gentle revision of intuition. You were taught that chemistry lives on a potential energy surface set by nuclei and electrons, with the electromagnetic field as a distant bookkeeper. Yet cavities make the field a participant, another reagent, whose concentration is measured not in moles, but in mirror finesse and mode volume. And once you accept that, you gain a new design space where geometry and color are as editable as temperature and pH. Leave this chapter with a sentence you could tell a careful skeptic. Polariton chemistry doesn't promise miracles. It offers a controllable way to hybridize molecular motion with confined light so that energy flows. Barriers and early-stage structure formation are nudged in measurable, sometimes useful ways, provided you respect the collective nature of the effect, build rigorous controls, and aim at problems where gentle edits to kinetics or selectivity are worth real value. If you keep that balance, tuning reactions with light stops sounding like magic and starts looking like good engineering. Rydberg molecules with stadium-size orbitals. Picture an atom swollen to absurdity, its outer electron wandering so far from the nucleus that a whole second atom, still in its ordinary ground state, can sit comfortably inside the orbit like a person standing on a field inside a stadium, and then realize that this is not a cartoon but a laboratory object. A Rydberg molecule, an ultra-long-range bond born not from the usual tug between charges but from the faint, frequent brushes of a very slow electron passing by a neutral neighbor and leaving behind just enough attraction to hold them together. To build good intuition, set aside the usual metal spring metaphors of chemical bonding and think of a vast, lumpy fog of electronic probability surrounding a tiny positive core. And imagine a second atom drifting through that fog at ultra-cold temperatures where motion is slow and collisions are gentle. Each time the Rydberg electron wanders near the passerby, it scatters a little, and the average of those countless soft nudges carves a shallow pocket in energy at certain distances, a pocket deep enough to trap the pair into a bound state, whose bond length is measured not in angstroms, but in hundreds of nanometers, even micrometers. Because the electron's wave is huge and structured, the shapes of these pockets vary wildly. In the simplest cases, They yield weakly bound S-wave dimers with oscillatory wells that mirror the radial ripples of the Rydberg orbit. While in more dramatic cases where the electrons scattering off the perturber resonates with higher partial waves, the bond supports trilobite and butterfly states, nicknames born from the maps of their electron density, which boast permanent dipole moments so enormous that a tiny external field can tilt or stretch the whole object with a flick. None of this requires heat or turbulence. Experiments form these molecules in gases cooled to microkelvin by shining a narrow laser that gently promotes one atom to a high principal state in the presence of a neighbor, then reading the spectrum for telltale lines shifted by a few megahertz to tens of megahertz below the bare atomic transition. A subtle red badge that says bound. Measured bond lengths can exceed the width of a human hair by factors of 1,000, yet the binding energies are shallower than many radio stations. A combination that feels almost paradoxical until you accept that the glue here is contact-like scattering averaged over a tremendous volume. This exotic bonding reveals simple, useful truths. By fitting those spectra, you can read off the low-energy scattering parameters of electrons on neutral atoms, quantities that are not easy to measure otherwise, and you can map how those parameters change near resonances as a function of collision energy, turning weird chemistry into precision scattering metrology. Because the electron cloud is giant, the molecule is hypersensitive to fields and to motion in the background gas. 1,000th of a volt per centimeter can shift levels measurably. A modest magnetic field can rethread the nodal pattern, and a stray atom drifting into the cloud can alter the energy as if you had tweaked a knob, which makes these objects both fragile and powerful as sensors. Their lifetimes sit in the microsecond to tens of microseconds range, limited by natural decay of the Rydberg state and by collisions that scramble phase or swap energy. So the game is to prepare and read quickly, to trap and image gently, and to choose principal numbers and host species that balance bond strength against survival. The most striking images in this field come not from cameras, but from the patterns of lines. By scanning laser frequency and external fields, you see families of bound states emerge and split, some tied to specific internuclear separations that echo the electron's radial nodes, others with huge dipole slopes that betray their trilobite nature, all of them acting like a fingerprint of the wave function's structure on scales your chemical intuition never needed before. Once you accept that a ground state atom can be a guest inside another atom's orbital, your imagination can climb. Place many ground state atoms in the electron cloud, and you get polyatomic versions with several guests sitting at favored distances, their energies adding and interfering so that the spectrum becomes a combinatorial ledger of who sits where. Embed the process in a Bose-Einstein condensate, and you can paint a picture of the condensate's density by the shift it imposes on the Rydberg line, essentially performing in situ microscopy with a single giant electron as the probe. Exploit the well-known blockade of Rydberg excitation, and you can control not only the number of giants you create, but also the proximity of potential partners, tuning the probability for molecule formation, like a chemist who can dial chance of meeting rather than concentration. Steer with fields, and you find that a trilobite's monstrous dipole lets you align the molecule in space, stacking them into ordered orientations or sorting different rotational states by their response, while gentle microwaves can couple bound vibrational levels within the same electronic manifold, turning the dimers into playgrounds for coherent control, where you move population among wells that are hundreds of nanometers apart. Technology angles are more than wishful thinking. These molecules' field sensitivity makes them candidates for small volume electric field probes that outclass neutral atom sensors in coupling strength. Their long baselines turn them into precise yardsticks for calibrating gradients, and their controllable dipoles suggest mediated interactions between distant qubits if hosted near superconducting devices or inside optical lattices designed to accept these giants without damage. The honesty list is as important as the promise. Thermal blackbody radiation at room temperature can nudge populations between neighboring Rydberg levels and shorten lifetimes. Motional heating from imperfect trapping blurs the spectroscopy, and background gases turn narrow lines into ragged shoulders unless you dig deep into vacuum and keep the sample clean. Molecules with strong higher partial wave character can be particularly sensitive to small details of the short-range potential, challenging models that ignore fine structure or hyperfine structure. So comparisons between theory and experiment must be careful about which approximations were made. Detection, too, is a craft. Field ionization is simple but destructive. Absorption imaging is gentle but demands cleanliness and high optical depth, and state-selective detection requires lasers stabilized to within a sliver of the already small binding energies. Still, the field's progress is steady and tangible. Cleaner lasers and colder gases produce sharper spectra and clearer assignment of states. Tailored excitation schemes create molecules in selected wells rather than indiscriminately across many, and external field knobs translate line shifts into direct measurements of polarizabilities and dipoles that anchor models. Perhaps the deepest lesson is conceptual and liberating. You were taught that chemical bonds come in a few flavors: ionic, covalent van der Waals. Yet here is a bond that is none of those in the usual sense, a bond whose glue is the average of gentle electron bumps spread over a region big enough to host dust, and that bond's parameters are not fixed by elemental identity alone, but by quantum size and the slow dance of scattering phases. That teaches humility about the categories we prefer, and suggests a broader view in which chemical means any stable arrangement of nuclei and electrons, allowed by the quantum rules and the environment we create. When you leave this chapter, be ready to tell a curious listener one crisp sentence. Rydberg molecules bind because a giant, slow electron corrals a neutral atom inside its orbit and, through repeated soft collisions, carves a shallow but real potential that holds them together at stadium scales, giving rise to dipoles of breathtaking size, spectra that read like maps of wave function structure, and tools for sensing and control that ride the edge between delicacy and grandeur. An honest, captivating corner of physics where chemistry discovers room it never knew it had. Rydberg dressing, designer interactions on demand. Imagine giving neutral atoms a faint aura, so subtle that they mostly stay themselves, yet potent enough that when two of them drift within a chosen distance, they feel a designer push or pull you dialed in advance, and you have the essence of Rydberg dressing, a way to turn feeble, short-range encounters into programmable, medium-range interactions that you can switch on, shape, and tune without ever fully promoting the atoms into fragile giant states. The trick is conceptually simple, though the execution is exacting. You shine a laser that nearly, but not quite, excites each atom to a highly excited Rydberg level, borrowing just a whisper of that level's enormous sensitivity and long reach, then returning it before the atom truly changes its identity. And this brief borrowing endows the original state with an interaction profile that looks like a soft plateau at short distances and fades away beyond a tunable radius. That soft core shape is the beating heart of the technique. When two dressed atoms are closer than your chosen radius, the interaction does not spike to infinity like a hard collision, but saturates at a controlled value, preventing runaway blockade while still deterring near neighbors. And when they are farther apart, the strength dies off smoothly with distance, letting you knit a lattice of influences that is neither strictly local nor completely global. Pick the detuning, the color offset of your laser, as the how far knob and the drive strength as the how hard knob, and you can place the plateau where you want and set its height, crafting effective forces that map to spin models with tunable range, to bosons that feel each other over many sites, or to mixtures where different species sense different radii. This is not hand-waving. Arrays of atoms held in microscopic tweezers or optical lattices have used dressing to draw phase diagrams on demand, shifting from nearly non-interacting gases to crystals of correlations with only a gentle change of power and color. In a dressed cloud, the onset of structure is not the violent snap of a phase transition driven by an abrupt blockade, but a graceful rebalancing where density waves and domains can form without one site completely freezing its neighbors, which is why theorists love dressing for emulating matter with competing tendencies, patterns that require interactions to be strong and finite at short range, yet persistent over several spacings. If you prefer a tactile picture, imagine you are the urban planner of a city where residents are encouraged to keep a respectful distance, but not forced into rigid grids. Within one house width, they feel a firm but not infinite repulsion that prevents crowding, and beyond a few houses the influence fades, allowing neighborhoods to self-organize into patterns that are neither clumped nor perfectly uniform. Experiments translate that civic metaphor into physics. In two-dimensional arrays of tweezers, dressed interactions have produced stripe and bubble orders, roton-like dips in collective motion that presage spatial patterning, and entangling gates that benefit from the soft plateau by being less sensitive to the exact placement of atoms. In Bose gases, weak dressing has softened the spectrum so that excitations at a finite wavelength become unusually easy, seeding supersolid behavior where superfluid flow coexists, with a gentle density modulation, a phenomenon once confined to helium law now realized in cold atoms by turning the interaction knob rather than the container's pressure. Why not simply excite fully to Rydberg states and enjoy even stronger forces? Because full excitation is a double-edged sword. It empowers spectacular interactions, but also invites fast decay, avalanche losses, and harsh blockades that make some algorithms brittle. Dressing asks for far less population in the giant level, often a few parts in 1,000. So scattering and spontaneous decay are reduced proportionally, and the many-body dynamics can unfold over longer, more programmable windows. The figure of merit you should keep in mind is a balance, interaction, strength times available coherence, versus all the bad actors that blur the phase. Off-resonant photon scattering, background radiation nudging levels, laser phase noise, and motion of atoms in their traps that scrambles phases across the array. Engineers treat this like budget planning. Raise power and you gain stronger coupling, but pay more in scattering and heating. Increase detuning and you reduce unwanted decay, but must drive longer to get the same effect. Sweet spots exist where the plateau height is big enough to matter, while the probability of a harmful jump remains small, and identifying those spots is the difference between pretty diagrams and reliable hardware. Practical recipes reflect this accounting. Choose high principal levels that offer long-reach sensitivity, but not so high that blackbody photons at room temperature shuttle population uncontrollably. Stabilize laser frequency so the near-miss to resonance stays a near-miss. Shape pulses with smooth ramps and carefully timed echoes that cancel slow drifts. And use magic trapping conditions or differential light shifts to keep the base state and its dressed partner aligned, so that the induced interaction does not wobble as atoms breathe in their tweezers. Verification is as concrete as the design. You measure the shift of one atom's transition when a neighbor is present at different separations to draw the soft core curve directly. You watch collective oscillations speed up or slow down as you vary atom spacing, and you compare results with and without dressing to isolate the effect. You entangle two atoms with a controlled phase that depends on how long you dress them and how far apart they sit. And you check the truth of that dependence by moving the tweezers like sliders on a mixing console. Once you trust the dial, uses branch out quickly. You can build multi-qubit gates that tolerate slight misplacements because the plateau makes the phase less sensitive to exact distance. You can simulate magnetism with frustration by designing radii that cause a spin to feel two neighbors nearly equally, encouraging patterns that ordinary nearest neighbor models cannot produce. You can squeeze metrological states by letting weak, all-to-all tails correlate many atoms just enough to beat standard noise without locking them into a single chunk. Even cross-platform bridges open. A dressed ensemble can act as a mediator between microwaves and optics by letting a tiny Rydberg fraction sense a microwave field and share that imprint with optical light through electromagnetically transparent channels, a hybrid tool for sensing over broad bandwidths. Honesty is essential here, because dressing is not free magic. Small admixtures can still lead to rare jumps into the full Rydberg state that trigger a cascade of losses if a stray ion forms and pulls neighbors over the edge. Power fluctuations can modulate the plateau height from shot to shot. Motional entanglement between internal states and trap vibrations can wash out the very correlations you seek unless the traps are deep and the timing is precise. And at higher densities, the gentle crossing of many soft cores can produce mean field shifts and inhomogeneities that blur coherent dynamics unless the array is uniform. The field has learned to tame these gremlins by spreading the interaction across time and space, rather than concentrating it in single, brutal pulses, multi-tone dressing that averages out sensitivity to drift, composite sequences that refocus phase errors, and dynamical decoupling that lets the desired interaction accumulate while slow noise cancels. Perhaps the most valuable intellectual shift you can take away is to stop thinking of interactions as immutable properties of a species and start thinking of them as software-defined features of a platform. By painting a small fraction of Rydberg character onto otherwise benign atoms, you write a line of code that says, each pair within this radius accumulates this phase per microsecond, and then you edit that line depending on the computation or material you want to emulate. This perspective is empowering because it turns the difficult task of building new particles into the more accessible task of crafting new Hamiltonians with light, one feature at a time, and it encourages a disciplined approach to honesty. Measure the scattering cost, document the coherence you truly have, and design protocols whose promised performance survives those realities. When you leave this chapter, keep one crisp sentence ready. Rydberg dressing borrows just enough of a giant state to give ordinary atoms tunable, medium-range interactions with a flat top and soft edges, enabling quantum gates and simulations that are both strong and gentle, so long as you balance the borrowed power against the price of decoherence, the way any careful engineer balances ambition against noise, synthetic gauge fields, and spin orbit in cold atoms. You've learned again and again that motion follows forces you can point to, gravity here, magnetism there. But there is a quieter truth you can test with your own hands in a cold atom lab. By writing phases into matter waves with light, you can make neutral atoms believe they carry charge and feel fields that don't exist in air. And by tying an atom's internal spin to its direction of travel, you can give it a preference for turning left or right without ever touching it. This is the craft of synthetic gauge fields and spin-orbit coupling in ultra-cold gases, where lasers, coils, and carefully timed gradients let you sculpt the rules of motion themselves rather than just the terrain, so that a gas of neutral atoms flows like electrons in a magnetic material, complete with edge currents, quantized vortices, and band structures that bend into shapes you normally only see in textbooks about solids. The starting insight is simple enough to live in your intuition. A quantum particle remembers the phase it accumulates as it moves, and if you engineer that phase to depend on position, the particle behaves as if a vector potential were present. In practice, you use Raman beams, two laser colors whose difference matches an atomic transition, to transfer a tiny kick of momentum whenever the atom flips between long-lived internal states. And because that flip also stamps a phase that varies in space, the atom's wave function picks up the same mathematical twist it would have felt from a magnetic field. Sweep the beams across a cloud and suddenly the dispersion curve, the simple parabola you expect for free motion, shifts sideways and sprouts minima at finite momentum. Your first signature that spin and motion are locked together, so that upspin prefers one direction and down the other. With careful geometry, you can go further and realize analogues of Dresselhaus or Rashba-like couplings in 2 dimensions, letting you test how spin textures wind around momentum space and how interactions respond when the lowest energy states sit on rings rather than points. Gauge fields that mimic large magnetic fluxes are built in a different but equally tactile way. You prepare atoms in an optical lattice and modulate the tunneling between sites with lasers that imprint a controllable phase every time a particle hops. So going around a tiny square multiplies phases into a net angle, the Piles phase, that stands in for a magnetic flux through that square. Stack many squares, and you grow a lattice threaded by a synthetic field, strong enough that each plaquette can carry a sizable fraction of a flux quantum, a regime impossible with real magnets at human scale, but routine with light. When you scan the energy of atoms moving through such a lattice, you can map out the famous butterfly pattern, bands splitting and recombining as flux grows, no graphics card required. Just time-of-flight images that reveal how population spreads across momentum. If lattices aren't your preference, you can coax similar physics by rotating a Bose-Einstein condensate so fast that Coriolis forces mimic Lorentz forces, one of the oldest routes to make neutral fluids act charged. But Raman-dressed and laser-assisted schemes give you the fine-grained phase control that rotation cannot match. The point of making these fields is not only beauty, it is access to topological bands that host chiral edge flow, to synthetic Hall effects without charge, and to spin momentum locking you can dial at will. With bosons, the field seed vortex lattices and, at strong coupling and low filling, open a path towards strongly correlated states that echo fractional quantum Hall liquids. With fermions, the spin-orbit link reshapes Fermi surfaces, modifies pairing channels, and allows you to explore superfluids whose order depends on direction, all in a clean, disorder-free setting where you control density, interactions, and geometry explicitly. Detection is concrete and visual. Release the atoms and read their momentum distribution to see shifted minima or ring-shaped ground states. Image in situ to watch vortices arrange into ordered lattices whose spacing matches the effective flux. Perform spin-resolved time of flight to map textures in momentum space, or reconstruct geometric properties directly by tracking how cloud populations evolve under slow parameter cycles, extracting Berry phases and curvatures not from calculation but from motion. You can even build an extra synthetic dimension by labeling several internal states as sites along an invisible axis and using Raman transitions as links between those sites, so that a 1D chain of real positions plus a handful of spin states becomes a 2D lattice threaded by a tunable flux, complete with edge states that live not at the chip's boundary, but at the ends of your internal state ladder. The engineering challenges are honest and fixable, rather than mystical. Every Raman photon you scatter risks heating the cloud and washing out coherence, so you choose transitions with minimal spontaneous emission. Clock states in alkali earth atoms are a favorite, and you detune far enough that atoms feel the momentum kick without soaking up real light. Laser phase noise and intensity drift can move the synthetic field under your feet, so you lock frequencies, stabilize paths, and arrange interferometric geometries that cancel common mode jitter. In lattices, imperfections in beam alignment and residual harmonic confinements can smear the elegant band patterns. So you flatten traps and calibrate link phases by watching interference from small loops before you scale up to larger patterns. And because these are effective fields, not the full electromagnetic law, you design carefully to respect gauge consistency where it matters. The phases around each loop must add exactly to the flux you intend, or else your magnet leaks. Once those nuts and bolts are tightened, the payoffs move from posters to protocols. You can route atoms around defects with edge channels that bypass scattering. You can switch between insulating and conducting behavior by dialing a phase knob rather than swapping materials. You can test how interactions reshape topological protection by strengthening or weakening contact forces with a Feshbach resonance and watching edge currents survive or fail. And you can prototype building blocks for atomtronic devices where current-carrying states circulate without resistance because geometry, not disorder, sets the rules. The real power for you as a learner is conceptual clarity. These experiments expose how force in quantum mechanics often means phase gradients, and how linking an internal label to motion gives you directionality without a push. A lesson that applies well beyond cold gases to photonics, mechanics, and even electronics designed with synthetic dimensions. If you step back for a final moment, notice the philosophical invitation. Rather than taking the world's fields as given, you are authoring them, deciding which loops carry phase and which motions are tied to identity, and then asking matter to live under those rules long enough for it to teach you what is robust, edge flow that shrugs at disorder, and what is delicate, coherence that vanishes under the wrong color of light. Carry this sentence out of the chapter and make it your own. By imprinting phases with lasers and tying spin to motion, you can make neutral atoms behave as if charged in a magnetic world and explore topological and spin-orbit physics with knobs that control geometry, strength, and purity, turning abstract band diagrams into living fluids that circulate, interfere, and remember the paths you drew for them. Beck BCS crossover and unitary fermions. Imagine watching a gas of identical, stubbornly independent fermions, particles that normally refuse to share a state, Slowly learn a partner dance as you turn an invisible knob, first pairing so tightly that each couple behaves like a single boson that condenses into a gentle, collective wave, then easing the grip until the partners drift far apart yet remain correlated, forming a superfluid made of overlapping pairs that are everywhere and nowhere at once. That smooth journey is the BEC-BCS crossover, and in the middle of it lies a special point called unitarity, where the interaction is as strong as quantum mechanics allows, without setting a length scale. So the gas forgets the details of the force and becomes universal, its properties determined only by density and temperature. Start on the left of this landscape with molecules. If attraction between two fermions is strong enough to bind them robustly, those dimers act like bosons that compile into the same low-energy state, creating a Bose-Einstein condensate, not of atoms, but of diatomic molecules, a superfluid whose behavior you can read with your intuition for dilute bosons. Coherence across the cloud, a single macroscopic wave function, quantized vortices when you rotate it. Now slide the knob toward weaker attraction and watch the character change without a sharp break. The bound state loosens. The size of a pair grows to rival and then exceed the average spacing between particles, and yet at low temperatures a superfluid survives because a sea of states near the Fermi surface allows Cooper pairs to form, extended couples stabilized not by deep binding, but by the collective structure of the many-body system. In this BCS-like regime, pairing and condensation happen essentially together at the superfluid transition, and the energy gap that protects flow from scattering is small compared to the Fermi energy, making the phase delicate but still remarkably robust when the gas is clean and cold. The intellectual beauty of the crossover is that nothing discontinuous happens as you tune from one side to the other. No latent heat, no abrupt order parameter jump, only a continuous evolution of pair size, excitation spectrum, and thermodynamic responses, so that textbook categories, molecule versus Cooper pair, reveal themselves as convenient labels for ends of a single thread. Pivot your attention to the center, the unitary regime, where the two bodies' scattering amplitude saturates and the scattering length blows up in theory, while the gas itself stays finite and stable in the lab. Here there is no meaningful notion of a pair size set by the interaction, and the only natural rulers are the interparticle spacing and the thermal wavelength. Because the system sheds microscopic details, macroscopic observables settle into simple patterns. A ground state energy proportional to that of a non-interacting Fermi gas times a universal number, a little under 1/2, a pressure and chemical potential that track with the same scaling, and a transition temperature that is a sizable fraction of the Fermi temperature. This universality is not a slogan, but a measured fact. Experimenters image the density profile in a gentle trap, infer local thermodynamics via the known shape of the confining potential, and collapse data from different atom numbers and trap strengths onto a single equation of state that matches calculations from quantum Monte Carlo methods. The unitary gas also flows in a way that borders on perfection. Its sheer viscosity at low temperatures drops to within a small multiple of quantum lower bounds, so that collective oscillations ring with weak damping and hydrodynamic expansion. After release from the trap, shows graceful elliptic flow reminiscent of exotic plasmas. Except here, the constituents are neutral atoms cooled to nanokelvin, dynamics at unitarity put on equally honest shows. Exciter breathing mode, and you find its frequency tied to the scale invariance of the equations of motion, a signature that the gas has no hidden length scale beyond what you impose. Rotate the cloud, and it sprouts quantized vortices whose orderly arrays let you count circulation one by one, a direct visual proof that superfluidity survives even when pairs are large and diffuse. Probe the gas with radio frequency or momentum resolved spectroscopy and you see evidence for pairing above the transition temperature, a smeared out gap or pseudo gap in the single particle spectrum, inviting comparisons to strongly correlated solids while reminding you that cold atoms offer a cleaner playground where disorder, lattice defects, and unknown phonons don't cloud the story. Getting to this regime in the lab is a triumph of control and restraint. You prepare two internal states of a fermionic species, cool by evaporation in optical traps that treat both states equally, and tune the interspecies attraction with an external field that moves a bound state in and out of alignment with the scattering continuum, thereby sweeping smoothly from deep binding to gentle Cooper pairing. You confirm superfluidity not by faith, but by smoking gun signatures, vortices that appear only below a critical temperature, sudden changes in moment of inertia, sharp shifts in collective mode frequencies, and phase-coherent interference when two clouds merge after a quench. You also learn hard truths about losses. Near the strongly interacting region, 3 atoms can collide and form a molecule while sending a third flying with the binding energy. So you shape densities and timescales to balance the desire for strong correlations with the need for stability, and you choose atomic species and spin mixtures that suppress the worst loss channels. Thermometry, a surprisingly thorny issue, is solved indirectly by comparing measured density profiles with universal equations of state, or by tracking how collective modes damp with temperature, since sticking a thermometer into a nanokelvin cloud is not an option. Beyond equilibrium lies a garden of non-equilibrium tests. Quench from one interaction value to another, and watch pair correlations grow in time, revealing how superfluid order coalesces. Ramp slowly through the transition, and measure the density of spontaneously formed vortices as a test of causality-limited ordering. Drive the gas with an oscillatory field and map transport coefficients, viscosity, spin diffusion, whose temperature dependence encodes the ease with which the fluid rearranges momentum and polarization. These are not only atomic curiosities. The unitary Fermi gas acts as a touchstone for any strongly interacting fermion system that lacks a small parameter, informing models of neutron-rich matter in the crust of stars where pairing among neutrons shapes thermal evolution, and offering a conceptual counterpoint to high-temperature superconductors where pseudogaps and short coherence lengths raise similar questions in dirtier settings. The crossover also has a compelling two-dimensional cousin, where pairing and phase coherence unbind at different temperatures through vortex physics, widening the window for fluctuating pairs and letting you test the role of reduced dimensionality cleanly. Though the details of universality shift because scale invariance behaves differently in a plane than in 3 dimensions, even in 3 dimensions, the simplicity of universality has boundaries you should respect. Finite effective range and the presence of additional internal states can bend the clean scaling at higher densities or near additional resonances, and inhomogeneous traps blur sharp features unless you use flat-bottom potentials or cleverly undo the blur in analysis. Yet within those limits the lessons are crisp. Superfluidity is not a single trick, but a continuum of behaviors stitched together by pairing, and the unitary point is a pole star where theories can be benchmarked because the system forgets what bonds look like in detail. If you want a picture to anchor this whole chapter, imagine sliding a focus ring on a camera. At one extreme, molecules are tight, crisp dots that condense into a smooth image. At the other extreme, pairs are broad, overlapping smears that still produce a coherent picture when seen as a whole. Right in between, nothing in the lens picks a preferred scale, and the scene organizes itself according to the density of points alone, a kind of honest clarity that is rare in strongly interacting physics. Leave with one sentence you can say to a skeptical friend: by tuning attraction in a 2-component Fermi gas, you can watch a superfluid morph continuously from a condensate of compact molecules to a sea of extended Cooper pairs. And at the midpoint, the unitary Fermi gas, its thermodynamics and flows become universal, set only by density and temperature, giving us a clean, measurable standard for what strongly interacting can mean without hiding behind complicated materials or guesswork. Feshbach resonances, tuning, interaction knobs. Imagine reaching into the quantum world with a single dial and deciding, almost at will, whether 2 colliding atoms should behave like polite strangers who barely notice each other, affectionate partners who bind on contact, or quarrelsome neighbors who push apart, and then realizing that the dial is nothing exotic at all but a magnetic field you can set with a power supply. That is the practical magic of Feshbach resonances, a way to tune interactions by aligning an internal molecular level with the energy of 2 free atoms so that, during a collision, They borrow a momentary identity as a molecule and scatter as if the force between them had been rewritten. The picture to hold in your mind is a two-lane highway. In the open lane, atoms approach as free particles and would normally pass with only a small nudge. While in the closed lane, blocked at long range, there sits a bound state at a slightly different internal configuration. By sweeping a magnetic field, you slide that bound state up and down in energy relative to the free atom lane. And when the energies nearly match the lanes, talk through a small gate. For the duration of the encounter, the pair can duck into the molecular identity and pop back out, a detour that dramatically amplifies how strongly they act on each other. In experiments, this shows up as a huge, controllable change in the low-energy scattering length, the simple number that summarizes whether collisions are effectively attractive, repulsive, or almost cancelled, and the change can span from small and positive, through infinite where interactions become scale-free to large and negative, with the sign flip occurring over a field range that can be broad and forgiving or narrow and razor-sharp depending on the species and the resonance. The broad versus narrow distinction is more than vocabulary. A broad resonance lets the open channel dominate the character of pairs and makes the tuned interaction behave smoothly with little memory of the closed lane, while a narrow one leaves fingerprints of the closed channel everywhere, including a strong energy dependence that matters for dynamics. Discovering and calibrating these dials is refreshingly hands-on. You load a cloud of ultra-cold atoms into an optical trap, sweep the magnetic field, and watch for sudden changes in expansion, for dramatic increases in three-body losses, where atoms vanish into molecules plus a hot bystander, or for shifts in spectral lines that mark the birth of a weakly bound dimer just below threshold. Plot those features versus field and you have a map. The center field where the resonance sits, its width, the gentle background interaction away from resonance, and the precise conversion between field and collision strength that becomes the lab's interaction handbook. Once the map is in your head, you can do more than vary a number. You can orchestrate processes, a slow sweep from the weakly interacting side into the region where a shallow dimer exists, associates atoms pairwise into long-lived molecules, which you can then transfer to deeply bound states with carefully phased lasers to make stable molecular gases at microkelvin temperatures. A rapid quench instead creates a non-equilibrium tangle of correlations, a test bed for how pairs form and break under sudden changes. In mixtures, a gentle push of the field controls miscibility, allowing you to mix or demix two species on demand, to stabilize droplets whose existence relies on a delicate balance between mean field attraction and quantum fluctuations, or to trigger collapse and revival cycles that teach you how interactions distribute energy through many modes. Beyond static properties, the resonance becomes a dynamic switch you can flip to test transport. At weak coupling, a cloud released from a trap expands like a gas of independent flyers, while near the tuned maximum it flows hydrodynamically, its shape evolving as if it were a single fluid with a viscosity you can extract from the damping of collective modes. None of this requires you to accept myths or ignore costs. Large interaction strength near the resonance also fuels inelastic channels, especially three-body recombination where two atoms form a molecule and kick a third out with the binding energy, so number loss and heating are the constant taxes you pay. The way around this is honest engineering, optimizing densities and timescales so you collect the physics you want before losses dominate, choosing spin states where recombination is suppressed, and working with species whose resonances are broad enough that the required fields are moderate and stable. Field control itself is an art. Magnetic noise and eddy currents smear the sharpness of the knob, so experimentalists use low-noise current supplies, water-cooled coils with minimal inductance, feed-forward cancellation of ripple, and independent calibration via radio frequency spectroscopy on well-known transitions to nail the conversion between amperes and Gauss down to parts in 1,000 or better. The range of playgrounds is wider than magnets alone suggest. Optical Feshbach resonances use laser light detuned near a molecular transition to mimic the same tuning, offering spatial patterns and faster switching at the price of photon scattering and heating in 1 dimension and 2 dimensions, confining atoms so tightly that their motion is restricted changes the very meaning of a resonance, leading to confinement induced, features where the interplay between geometry and interaction produces strong coupling even when the three-dimensional knob is set to polite, bring the field to the edge of resonance, and a procession of fragile three-body-bound states predicted decades ago. Efimov states emerges in a geometric ladder, visible as repeated peaks in loss at fields where the scattering length takes special values. Those signatures are not only curiosities, but calibration points that anchor theory to data and allow precision comparisons across species. On the modeling side, you don't need all the microscopic details to work productively. A simple two-channel framework captures the essentials, an open channel describing free atoms, and a closed channel with a bare molecular level coupled by a matrix element. And from it flow the rules of the knob, how the scattering length varies with field, how the resonance width relates to the strength of channel coupling, how an effective range parameter becomes relevant for narrow cases, and how much of a dressed dimer's identity lives in the closed channel versus the open one, which matters for how the dimer interacts with light or with other atoms. This modeling is not just for theorists. It directly informs pulse shapes for molecule association, the choice of levels for optical transfers, and the interpretation of lifetime data. Applications branch quickly once you respect the boundaries. In atomic clocks and precision sensors, moving slightly away from resonances can cancel unwanted mean field shifts and stabilize performance. In quantum simulation with lattices, local control of the field across a pattern chip lets you create patches with different interaction strengths and study how transport crosses interfaces. In molecule formation, pairing via a magnetic sweep followed by coherent optical transfer has produced samples of deeply bound dipolar molecules whose collisions and long-range forces are research topics in their own right. And in strongly interacting Fermi gases, the same knob that tunes two body scattering maps out the entire path from weak pairing to tightly bound dimers and pins. The universal point in the middle where theory and experiment meet on equal footing. Equally important are the lessons from failed attempts. Sweep too slowly through a loss-prone region and your cloud dwindles. Sweep too fast and non-adiabatic defects populate excitations you didn't mean to create. Pulsing in a noisy field decorrelates your pairs. Holding at high fields without careful thermal management cooks your vacuum windows. Each misstep teaches why the knob is powerful only when turned with respect for timescales and noise budgets. Perhaps the most liberating habit to keep is to think of interactions as a resource you allocate rather than a property you suffer. By learning the resonance map of your species and mastering the hardware that sets the field, you decide when attraction helps you create molecules, when repulsion stabilizes a mixture, when strong coupling reveals hydrodynamics, and when neutrality preserves coherence. And when someone asks for the one-sentence takeaway, you can offer it plainly. A Feshbach resonance lets you tune how strongly ultra-cold atoms collide by aligning a hidden molecular level with their free motion, turning a magnetic field into a precise interaction knob that enables molecule creation, phase control, and universal many-body physics, so long as you balance the gain in coupling against the honest costs of loss and heat that come with opening the gate between lanes. Anderson localization of matter waves. Imagine setting a cloud of ultra-cold atoms free and expecting it to spread like perfume in a room, first quickly, then more slowly as density drops, only to discover that, in the presence of a carefully prepared disorder, the cloud stops, holds its shape, and refuses to wander, as if the landscape had quietly taught the waves to fold back on themselves. That stubborn stillness is Anderson localization for matter waves, a purely wave-borne arrest of transport that needs no walls, no traps, and no friction, only the repeated scattering and self-interference that a disordered potential provides. And once you see it with your own eyes, the usual story of motion equals force acquires a new chapter where motion equals phase memory. The physical picture is best approached with simple steps. When a coherent wave meets a random arrangement of bumps and dips, it scatters along many paths, and those paths recombine with phases that are not random at all. Certain loops favor constructive interference for returning to where you started, and destructive interference for escaping far away. So the probability to diffuse drops exponentially with distance beyond a scale called the localization length. With atoms, we can tune every knob that matters, make a one-dimensional guide with a random pattern, and, in theory, every single state is localized. So even a gentle initial push produces a stationary, lumpy profile in time. Move to 2 dimensions, and localization is still generic, but the length can be enormous, making it a game of patience and purity. In 3 dimensions, the story sharpens with a threshold. Below a critical energy, the states are localized. Above it, they extend. And the dividing line is the mobility edge, a concept that gives you a practical test. Prepare atoms with a narrow energy and watch whether their expansion saturates, localized, or keeps growing, extended. Experimentalists build the disorder honestly rather than as a cartoon. Shine a laser through a diffuser to make a speckle pattern whose bright grains and dark hollows act as a random potential. Or superimpose 2 incommensurate optical lattices to create a quasi-periodic landscape that mimics disorder while keeping exquisite control over its amplitude and correlation length. Then they release a Bose-Einstein condensate or a Fermi gas into that landscape and observe the time evolution. If you plot the density after many milliseconds, a localized component remains near the origin with tails that decay faster than any power law, while any high energy fraction above the mobility edge, if present, continues to drift outward, creating a 2-piece profile that reveals both localized and extended states at once. The key is to separate quantum interference from classical hindrance. Classical percolation would predict blocked flow only if the potential barriers form disconnected pockets. But in these experiments, atoms halt even when there are classically open pathways because the halting comes from destructive interference, not from blocked geometry, and you can prove it by changing the phase coherence. Add controlled dephasing with a noisy beam, or warm the atoms to shorten their phase memory, and the stationary profile melts into ordinary diffusion. Different platforms offer complementary vantage points. In the kicked rotor, you do not disorder space at all. You periodically kick atoms with a pulsed lattice in a way that translates into disorder in momentum space. And instead of cloud size in real space, you watch momentum stop broadening, a momentum space localization that maps mathematically onto the same phenomenon. In quasi-periodic lattices, the Aubry-André setting, you see a crisp transition as the relative lattice amplitude crosses a calculable threshold, giving you a clean dial to compare with theory. With true 3-dimensional speckle, you can sweep the disorder strength and energy and extract a mobility edge from where expansion flips character. A rare chance to measure a phase diagram of transport in a system whose interactions and temperature you control at will. Because atoms can interact, you get to ask a deeper question that condensed matter textbooks usually sidestep. What do weak interactions do to a localized wave? The answer is nuanced and measurable. Repulsive interactions can enable slow, subdiffusive spreading by letting excitations exchange energy, turning a rigid halt into a creeping expansion, with a time law much slower than diffusion, while strong, attractive interactions can create self-trapped structures that superficially look localized but arise from non-linearity, not interference, so careful diagnostics. Interaction quenches, measurements of coherence, response to dephasing are essential to separate true Anderson physics from mean field self-trapping. Honest experimental signatures go beyond pretty pictures. You can quantify localization length by fitting spatial tails. You can measure the return probability by pulsing the atoms and asking how many come back to a small region after a delay. You can probe spectral features with modulation spectroscopy to find gaps and resonances that mark localized regimes. And you can look for the hallmark of coherent backscattering and enhancement of scattering into the reverse. Direction, which is a direct optical analog telling you that time reversed, paths are interfering constructively in favor of return. Details matter in ways that teach you design. The speckle's correlation length sets a preferred scattering momentum. So if your atoms are too cold or too hot compared to that scale, localization weakens. Blue detuned speckle, atoms attracted to dark regions, and red detuned speckle, atoms attracted to bright grains. produce different statistics of barriers and wells, which changes how easily waves can sneak through by tunneling. Finite temperature sprinkles a spread of energies across the sample, so the same cloud can be partly localized and partly extended, which is why carefully prepared narrow energy distributions, achieved by evaporative cooling and energy selection, sharpen the observation. And any residual harmonic confinement from your traps can imitate a stationary profile unless you remove or flatten it, reminding you that localization should be diagnosed in a truly free expansion, or with potentials whose curvature is known and accounted for. Philosophically, Anderson localization teaches two durable lessons. First, that disorder is not merely a nuisance, but a structural element that can sculpt transport in rigorous, predictable ways. Second, that interference is a form of order that does not need periodicity. Randomness can host coherent patterns if the phase is preserved. Those lessons echo across other wave systems. Light can localize in disordered photonic crystals, sound in acoustic networks, even microwaves in random cavities. And cold atoms give you the cleanest handle because you can dial interactions to near zero, freeze out phonons, and decide which dimensions to explore. The frontier now blends precision and ambition, measuring critical exponents near the mobility edge by tracking how localization length diverges as you tune disorder, studying how a small amount of controlled dephasing rounds the transition in a universal way, and mapping the crossover from single particle localization to many-body localization when interactions are present, but energy is conserved in a closed system. Throughout, the discipline remains the same. Test against classical models to rule out trapping. Vary coherence deliberately to prove the interference origin, and use independent diagnostics, real space profiles, momentum distributions, coherent backscattering, to make the case robust. Walk away with this practical guidance you could apply tomorrow. If you want to see matter waves refuse to spread, give them a disordered potential with a correlation length suited to their energy. Prepare them coherently and cold. Eliminate spurious confinement, and watch for stationary exponential tails that survive small nudges yet dissolve under deliberate dephasing. And carry a closing thought that slows the mind while sharpening the eye. Sometimes, the surest way to stop motion is not to build a wall, but to let the traveler meet too many forks. So many that the echoes of its own footsteps cancel the urge to roam. An elegant reminder that in the quantum world, stillness can be the most coherent form of movement. Twisted belayer graphene and flat band, magic tilt one sheet of graphene by a whisper against its twin and a moiré. Landscape blooms, a gentle interference painting, whose length scale is tens of nanometers rather than angstroms. And if you keep turning that angle down to about 1 degree, you watch the kinetic energy of certain electrons fade until it is so small that interactions, usually the background chatter, become the main voice. That is the flat band magic of twisted bilayer graphene. Two atom-thin lattices rotated by a tiny twist produce electronic bands whose dispersion nearly vanishes at so-called magic angles, most famously near 1.1 deGauss. And in that slow-motion band structure, a small push from repulsion or attraction can steer the entire many-body story, spawning correlated insulators, superconductors, orbital ferromagnets, and even quantized Hall behavior without an external magnetic field. The scientific bones beneath the spectacle are accessible if you start with a simple picture. Each monolayer hosts Dirac cones, linear crossings where electrons behave like massless particles, and twisting the layers overlays those cones in momentum space. The resulting moiré periodicity folds the Brillouin zone into a smaller mini-zone. An interlayer hybridization opens gaps and rearranges velocities until, at special angles, the effective bandwidth of the low-energy moiré bands collapses to just a few millielectron volts. When bandwidth shrinks while the Coulomb scale set by electron-electron interactions barely changes, the ratio flips in favor of interaction. So filling those narrow bands with a fraction of an electron per moiré cell becomes more like arranging seats at a crowded dinner than like populating plane waves. Who sits next to whom matters, and phases you don't see in ordinary graphene emerge because the system can lower its energy by organizing collectively. Transport through such a device, fabricated by tearing and stacking flakes with polymer stamps and flattening bubbles under modest heat, reveals this reorganization starkly. Tune a gate so that the moiré flat band is half filled and the resistance can jump, signaling a correlated insulating state where electrons lock into a pattern that blocks motion. Nudge the filling slightly away and domes of superconductivity rise on either side, with critical temperatures of a few Kelvin and critical fields that suggest short coherence lengths, all hallmarks of pairing, driven not by a crystalline lattice's vibrations alone, but by an interplay where soft phonons in the moiré, electronic correlations, and perhaps even valley and sublattice fluctuations conspire. You read these phases in Landau fan diagrams, the fanning pattern of quantum oscillations as you vary magnetic field and carrier density. Degeneracies break, slopes change, and sequences reveal whether spin, valley, or sublattice flavors are frozen or free. Capacitance and compressibility measurements add texture, mapping where the electronic fluid is easy or hard to squeeze and showing cascades. Step-like reorganizations with filling that are difficult to reconcile with a purely single-particle picture. Scanning tunneling microscopes put an eye directly on the density of states, finding sharp peaks near charge neutrality, evidence of Van Hove singularities reshaped by the moiré, and local variations tied to minute twist angle inhomogeneity or heterostrain that can make one region superconduct while a neighbor leans insulating. When you align one graphene sheet with a hexagonal boron nitride substrate, another layer of control appears. The broken sublattice symmetry gaps the Dirac cones and endows the moiré bands with non-trivial topology. So at certain fractional fillings you find orbital ferromagnets and quantum anomalous Hall states with Chern numbers +1, detected not just by a plateau in Hall conductance, but by hysteretic magnetization loops that scream intrinsic magnet even at tiny fields. The theoretical landscape, honestly, is still a wrestling match of good ideas. Weak coupling approaches see nesting and enhanced density of states feeding spin or valley fluctuation mediated pairing, while strong coupling pictures start from localized charges on the moiré lattice and derive effective spin valley models whose exchange favors unconventional superconductivity. Phonons are not out of the story. Flattened bands amplify electron-phonon coupling, yet simple isotope shifts and the sensitivity of phases to screening and displacement. Fields hint that purely phononic glue cannot be the whole answer. What deepens your understanding and keeps the field grounded are the knobs you can turn and the ways the system answers. Adjust displacement fields with top and bottom gates to skew charge toward one layer, and the phase diagram reshapes. Introduce a few tenths of a percent heterostrain, and the flatness and symmetry of the bands alter enough to tilt the balance between superconductivity and insulation. Heat treatment that relaxes the stack can slightly change the local twist, moving devices on or off resonance with the magic angle, and careful four-terminal measurements separate intrinsic behavior from contact artifacts. Even the geometry of contacts and the cleanliness of the edges matter because current can percolate along pneumatic domains, regions where rotational symmetry breaks, and the resistance depends on direction, signaling that electrons sometimes choose stripes over uniformity across variants, twisted double bilayers, multilayers with alternating twists, and moiré materials built from transition metal dichalcogenidase. You see the same grammar with new vocabulary: flat bands, flavor degeneracies, displacement field tuning, ferromagnetism of orbital origin, and in certain TMD systems, electrically switchable topological gaps that uplift the idea from a single platform to a broader method for writing correlated phases with geometry. The limitations and the honesty they demand are just as instructive. Twist angle inhomogeneity over tens of microns means a single device can host multiple local phase diagrams. Disorder fills the flat band with in-gap states that can mimic metallicity. Strain fields and alignment moirés add mini-gaps and replica bands that complicate interpretation if you rely on one measurement alone. And the infamous sensitivity to fabrication means that two nominally identical stacks can host different strengths of correlation. A reminder that flat is a spectrum, and that a band a few MeV wide in a calculation can broaden in reality unless your device quiets the rough edges. For learning and for design, a practical mental checklist helps. To chase superconductivity, aim for twist uniformity near the magic angle and keep residual disorder low. Map compressibility to find where interactions dominate before you chase domes. Test for nematicity by rotating contacts or the sample and checking anisotropy. Apply small out-of-plane fields to see whether churn signatures or hysteresis appear, which would flag orbital ferromagnetism, and take seriously the role of screening from nearby gates, which can tame or enhance correlation strength depending on distance. Philosophically, this platform invites you to reconsider what a material is. Not just a chemical composition set in a furnace, but a geometry and a phase pattern you program with angle, alignment, and electric fields, where the same carbon atoms host band insulators, metals, magnets, and superconductors depending on how patiently you align them. It also challenges your intuition about cause and effect in condensed matter. Instead of tracking a fixed lattice that dictates electronic life, you are shaping the electronic life that in turn selects its own symmetry. Sometimes rotationally breaking into nematic order, sometimes polarizing a valley flavor to earn a churn number, sometimes weaving pairs whose phase stiffness is fragile and yet coherent. As you step away, carry a succinct truth you could hand to a skeptical friend. By twisting two graphene layers to a magic angle, you flatten electronic bands so that interactions outweigh motion. And in that moire-made landscape, you can gate tune between correlated insulators, unconventional superconductors, and topological ferromagnets, results that are real, reproducible with careful fabrication, and revealing of a bigger lesson that geometry, not just chemistry, is a powerful lever for writing the rules that electrons follow. Excitant condensates and counterflow. Imagine separating negative and positive charges into two nearby but electrically isolated layers and then coaxing them to fall in love across the gap so that each electron binds a partner hole in the other sheet, and instead of acting like two conductors, the pairings collectively behave like a single, neutral fluid that can slide without friction when the two layers are driven in opposite directions. That is the intuition behind excitant condensates and the striking transport signature called counterflow, where equal and opposite currents in the two layers move with vanishing resistance because the thing actually flowing is not charge alone but bound, electron-hole pairs whose center of mass carries no net charge at all. To make that picture concrete, start with how you build the pairs. In semiconductor double quantum wells, in atomically thin materials stacked into van der Waals heterostructures, or in quantum Hall bilayers under strong magnetic fields, you place electrons in one layer and leave the neighboring layer hungry for electrons so that each missing electron, a hole, forms an attractive partner for one next door. If the spacing is small enough for Coulomb attraction to matter, yet large enough to suppress direct tunneling that would prematurely recombine the pair, and if temperature is low enough that thermal agitation cannot rip them apart, the system enters a regime where the lowest energy description is no longer two separate Fermi seas, but a sea of composite bosons, excitons, capable of condensing into a macroscopically coherent state. The clue that you have crossed that line does not come from a pretty interference picture, but from transport that refuses to behave classically. Wire the two layers so that the top carries current to the right, while the bottom carries the same current to the left, and the measured resistance plunges because an exciton moving right in one layer necessarily implies its partner hole. Equivalently, an electron deficit moving right in the other, which is indistinguishable from real electrons moving left there. The pair slides as one object through the combined system, leaving little room for ordinary dissipation, and the voltage drops that would normally appear in each layer nearly cancel. Flip the geometry to drag mode, where you drive current in one layer and leave the other open circuit, and a surprisingly large voltage appears in the passive layer with a sign that tracks the formation of pairs rather than simple momentum sharing, a fingerprint known as perfect or near-perfect Coulomb drag when conditions are ideal. In quantum Hall bilayers at total filling 1, the phenomenon sharpens further. Each layer on its own would be a poorly conducting, gapped state, but taken together with strong interlayer correlations, they develop a phase that conducts counterflow supercurrents around the boundary while showing unusual Hall responses, including Hall voltages that cancel in counterflow and add in coflow in ways no single particle picture anticipates. Tunnel a little current between the layers and you see a sharp, almost dissipationless peak near zero bias, a Josephson-like response that whispers phase coherence across the gap. Again, not because particles physically move from one layer to the other en masse, but because the condensate establishes a common phase that makes small tunneling act like twisting a single order parameter. Outside high fields, atomically thin stacks, graphene double layers separated by a few atomic spaces, or transition metal, dichalcogenide bilayers forming tightly bound, long-lived indirect excitons with dipole moments oriented across the gap, provide a cleaner stage. Electrons and holes can be tuned by gates with exquisite precision. The spacing is literally a few nanometers of a chosen insulator, and moire patterns can corral excitons into arrays where interactions are enhanced. In such platforms, evidence for condensate behavior comes from steep rises in drag at low temperature, from counterflow that remains mobile while ordinary parallel currents remain resistive, and from critical currents and breakdown fields that track the expected stiffness of a neutral superfluid. To keep your understanding honest, gather the reasons this is difficult and how experiments navigate them. Recombination is the mortal enemy. If an electron can tunnel and annihilate its partner, the pair never lives long enough to join the dance. So fabrication seeks clean, pinhole-free barriers that are thin enough to preserve strong attraction, but thick or misaligned enough to quench direct tunneling. Disorder matters because excitons are neutral but not blind, and random potential variations can pin or fragment the condensate, converting graceful flow into creep unless density and uniformity are carefully controlled. Screening by nearby metals and gates tempers the very attraction that creates pairing. So device design balances the need for electrostatic control with the need to keep fields alive across the gap. Heating from measurement currents at millikelvin temperatures can masquerade as dissipation, demanding four-terminal geometries, minimal excitation, and careful comparison of coflow versus counterflow. And in systems without a magnetic field, the condensate may undergo a two-dimensional vortex unbinding transition. So the smoking guns are not infinite conductivity, but sharp changes in slope and nonlinear current voltage characteristics near a critical temperature that reflect the birth or death of phase stiffness. The conceptual payoff extends beyond a single material class. A condensate of excitons is a neutral superfluid whose flow can be steered electrically, which means you can imagine circuitry where information moves in the relative current between layers with tiny power dissipation, interconnects that do not spew heat because the moving quantity does not carry net charge, and hybrid links where optically created excitons in one region couple to electrically created pairs in another, bridging photonics and electronics without the usual conversion losses. Sensing ideas bloom too, because each pair has an electric dipole across the barrier. Tiny external fields or strains that skew the layers differentially can tilt the energy landscape for the condensate and be read out as shifts in critical current or drag, enabling compact detectors that respond to gradients rather than absolute fields. As for distinctions, keep one in mind to avoid confusion with nearby topics. Exciton condensates in bare electronic layers are not the same as exciton. Polaritons in microcavities that borrow a photon identity and condense at higher temperatures with shorter lifetimes. Both are fascinating, but the transport signatures we have dwelled on, counterflow superfluidity, near-perfect drag, Josephson-like tunneling between layers, belong to electronically bound pairs whose phase coherence spans an insulating spacer. When you try to falsify the story, the tests are concrete. Remove the balance between electron and hole densities, and the drag drops, and the counterflow resistance grows, as it must if pairing is the engine. Raise temperature and watch the counterflow channel lose its low dissipation advantage near a well-defined scale. Introduce a controlled disorder or a small interlayer tunneling and map how the critical current, the zero bias peak, and the Hall responses degrade. So you can separate an honest condensate from a tricky percolation network or a noisy junction. Different platforms then become comparative anatomy. Quantum Hall bilayers showcase topological edges married to neutral superflow. Graphene double layers highlight tunability and the possibility of roomier phase space at accessible fields. TMD hetero bilayers trade longer exciton lifetimes and strong dipoles for challenges in mobility and uniformity, with moire potentials offering a handle to pin or purposely pattern superfluid order. Through all of this, the most durable mental shift is to stop thinking of current as something carried only by charged particles in a single wire and start thinking of it as a two-channel story where neutrality can move while charge stays put. A division of labor that Mother Nature allows whenever pairing across a barrier is both strong and coherent. Leave with a sentence you can offer to a skeptic. Exciton condensates turn two coupled layers into a single neutral superfluid that reveals itself by frictionless counterflow, near-perfect drag and coherent tunneling features. And while the recipe demands cold devices, clean barriers and patient measurements, the results are hard, testable, and point toward a class of electronics where the quiet motion of bound pairs does the work that hot electrons do today. Nanoscale quantum thermometry. Start by imagining something as ordinary as a thermometer, then shrink it until the sensor is a single defect in a crystal or a tiny quantum dot smaller than a virus. And let it listen not to mercury expanding, but to how its own quantum clock ticks. Because nanoscale quantum thermometry is precisely that. You place a quantum system whose internal rhythm depends on temperature into a landscape of hot spots and cold eddies, and you read its frequency, brightness, or spin relaxation to learn how heat actually moves when the world gets small. The most widely used example hides in common diamond, a nitrogen vacancy center, a pair made from one missing carbon atom beside a nitrogen impurity, forms a spin system that you can address with green light and microwaves and read out optically, and the spacing between its spin levels, the zero field splitting, shifts predictably with temperature as the diamond lattice breathes. You prepare the spin in a superposition, let it evolve briefly like a tiny wristwatch, and measure its phase or resonance frequency by optically detected magnetic resonance. So temperature becomes a number extracted from a fit rather than from a color change on a strip. By planting many such centers near the surface of a diamond chip and scanning it above a device, or by grafting diamond nanoparticles into a living cell, you can map temperature with submicron resolution and millikelvin sensitivity, watching heat spill from a transistor gate under bias, or tracing the warmth around a mitochondrion as it turns chemical fuel into work. The science behind that simple readout is concrete and accessible. Temperature perturbs the lattice vibrations, phonons, which in turn modulate the crystal field felt by the defect, nudging its internal levels a little closer or farther apart. If you measure a resonance frequency, you need fewer photons and reach good sensitivity quickly, but must worry about stray magnetic fields that mimic the same shift. So you design pulse sequences that subtract magnetic noise while keeping the temperature signal. Or you choose double quantum transitions that respond strongly to temperature but weakly to magnetic drifts. If instead you monitor the spin's tendency to forget its state, the relaxation time that shortens as the thermal bath gets livelier, you gain immunity to slow magnetic wonder but trade it for a greater need to model the local environment. Either way, the sensors back action and the measurements overhead matter at these scales. The very light you use to pump and read out can heat the sample by tens of millikelvin if you are careless. So you trim duty cycles, spread power across time with pulsed schemes, and calibrate the readout warms by this much, offset using reference spots that should not change. The second family of thermometers replaces spins with light-emitting particles, upconversion nanoparticles, quantum dots, or rare earth-doped crystals have pairs of optical lines whose intensity ratio or separation drifts with temperature because two closely spaced excited states share the same ground. Excite them gently and you can read temperature from a pure intensity ratio that self-normalizes against fouling and focus, drift, a gift in biological environments. Yet the very chemistry that makes them bright can also change with pH or ionic strength. so controls matter. Verify that what you call temperature is not a change in local chemistry by checking a second chemistry-insensitive marker or by measuring the same spot with an independent sensor. For scanning probe work, you can graft a single quantum sensor onto the tip of an atomic force microscope and raster it above a circuit, reading the local temperature rise under alternating current drive and reconstructing thermal conductivity and boundary resistance across materials and interfaces. Those images end myths quickly. Heat does not flow uniformly from a hot line into a cold plane. Grain boundaries, voids and buried layers redirect it, creating bright and dark rivers that explain why two ostensibly identical devices age differently. When the target is a biological sample, honesty changes shape but not importance. Label uptake is not uniform. Endosomes can trap your particles at pH that shifts spectra, and the cytoplasm's refractive index tinkers with brightness. The cure is to combine modalities. Use the quantum sensor's ratio readout for temperature, a fluorescent lifetime marker to flag pH, and independent metabolic probes to correlate heat with activity, so the map you show traces heat, not chemistry. Beneath all platforms runs the same metrology logic. The smallest temperature you can resolve per square root timescales with how strongly the sensor's signal shifts with temperature, with how long you can preserve quantum phase or excited state population before noise blurs it, and with how many photons you collect. You increase sensitivity by improving photon collection with solid immersion lenses and photonic structures, by boosting coherence with dynamical decoupling pulses that cancel slow noise, and by choosing host crystals with fewer stray spins in the lattice. But there is a ceiling you cannot climb through. The quantum system must interact with its environment to sense it, and that interaction is the same channel that erases information. So there is a point where pumping harder or listening longer no longer helps, a practical face of the general limits on parameter estimation. Engineering choices turn those limits from abstractions into knobs. A shallow NV center, just a few nanometers from the surface, reads temperature right where heat enters or leaves, but suffers from surface charge noise. A deeper one lives in a calmer field, but averages over a thicker layer. A long, narrow averaging time, microseconds for Ramsey interferometry or milliseconds for spin relaxometry, distinguishes fast flicker from slow drift, which matters if you want to image transients like a transistor's first microseconds after switching. Calibration anchors the whole enterprise to reality. Your sensor tells you a frequency or an intensity ratio. To turn that into Kelvin, you measure the same quantity at known temperatures in the exact environment of use, preferably against a traceable standard like a calibrated thermistor attached nearby, and you revisit that calibration across days to learn drift. In microelectronics, this discipline pays off directly. By placing a diamond membrane over a functioning chip and using a wide-field camera to read many centers at once, labs have produced kilohertz rate movies of heat during workload bursts, revealing which interconnects act like hidden resistors and how effectively heat crosses chip package interfaces. The same techniques on the tips of scanning probes have quantified thermal boundary, resistance at metal dielectric, interfaces one location at a time, numbers, designers, normally infer indirectly, guiding choices about barrier layers and adhesion that save real devices from slow failure. In biology, quantum thermometers have challenged assumptions about average cell temperature by showing that metabolism creates submicron hotspots that persist for hundreds of milliseconds. Yet they have also exposed the danger of wishful seeing. Thicker cytoplasm or clustered probes can mimic warmth, so the strongest studies pair temperature maps with motion tracking, optical clearing, and concurrent oxygen consumption to prove causality. Alternative quantum platforms are maturing alongside diamond. Silicon carbide hosts color centers with similar spin readout, but at wavelengths friendlier for tissue, and rare earth ions in nanoparticles offer sharp, narrow lines and long memory that dovetail with multiplexed imaging. Even superconducting circuits use quantum thermometry when they read the occupation of a microwave resonator to extract the effective temperature of a single mode, a different regime. But the same philosophy of let a quantum degree of freedom be the probe. Where does it go next? Toward less invasive and faster. All optical protocols that read temperature from fluorescence alone avoid microwaves near delicate samples. Fiber-integrated tips bring nanoscale thermometry into confined spaces, and cryogenic-compatible sensors let you map heat in quantum processors, where each stray photon can derail computation. The conceptual lesson you should carry is crisp and useful. At the nanoscale, temperature is not a number smeared evenly across space and time, but a field with structure and memory. And quantum thermometers turn that field into data by letting a tiny system's timing or brightness be your measure. If you leave this chapter with one practical checklist, make it this: minimize measurement-induced heating, choose a sensor whose signal is specific to temperature in your chemistry, perform in situ calibration under the same optical power and environment, and use controls that can falsify your own interpretation. And with one reflection: good temperature maps are not pictures of color, they are stories of energy flow. And when you can tell those stories at the scale where devices fail and life happens, you stop guessing where heat goes and you start designing with it. Squeezed light metrology beyond shot noise. What if you could listen to a whisper by deciding in advance which kind of randomness you'll ignore, tilting the noise so that the uncertainty falls quiet exactly where your measurement lives, and then accept a bit more chaos in a direction you do not care about? That selective hush is the idea behind squeezed light metrology beyond shot noise, where you do not try to fight quantum fluctuations wholesale, but reshape them, so the particular combination of amplitude and phase that carries your signal is calmer than nature's default. Start from the honest baseline. In ordinary light, even a perfect laser, the arrival of photons jitters randomly, and that jitter sets a floor, the shot noise limit, under which simple averaging cannot go for a given power and bandwidth. The key realization is that the randomness is not featureless. It lives in two conjugate quadratures that you can think of as two dials on a rotating compass, one linked to amplitude and the other to phase. And quantum mechanics only insists that the overall area of uncertainty not shrink below a certain size. It does not forbid you from squeezing that area into a skinny ellipse by reducing fluctuations along one dial while allowing them to swell along the orthogonal dial. You generate such light by letting pump photons interact in a nonlinear medium so that they spontaneously split into correlated siblings, a process built with crystals that have engineered responses or with atomic vapors that support four-wave mixing. Below threshold, the device does not blaze with brightness. It quietly emits correlated vacuum fluctuations, squeezed vacuum, that carry no average light but carry less noise in the chosen quadrature. And when you overlay that onto your bright beam with a beam splitter and a carefully phased local oscillator, you create an output whose noise in the measurement channel falls below shot noise, even though your average power is unchanged. The simplest use is phase sensing. If what you care about is a tiny phase shift impressed by a weak signal, say the stretch of space-time in a kilometer-scale interferometer or the refractive twitch of a sample in a microscope, you align the squeezed quadrature with phase and accept extra noise in amplitude, which your readout discards. When your signals extend over many frequencies, a new wrinkle appears because the kind of quantum noise that dominates depends on frequency. At audio-like bands, radiation pressure noise, random kicks from fluctuating photon numbers, can shake mirrors and add displacement, while at higher bands it is the counting noise of the readout that dominates. This is where frequency-dependent squeezing matters. Rotating the ellipse as a function of frequency with the help of filter cavities so that you hush amplitude-like fluctuations where back action hurts and hush phase-like fluctuations where shot noise rules, a choreography that has already delivered real sensitivity gains in gravitational wave detectors that now listen deeper into the universe because their dark port is filled not with emptiness but with shaped vacuum. The same strategy scales down to tabletop sensors. In balanced homodyne, detection for spectroscopy, Squeezed light reduces the noise floor for tiny absorption or dispersion signals without increasing sample illumination, which is essential when doses must stay low. In optical magnetometers, injecting squeezing into the readout beam lowers photon shot noise so that atomic projection noise becomes the next hurdle, letting you separate what is limited by atoms from what is limited by light. In biological imaging, where bright light damages tissue, squeezing lets you extract the same contrast at lower power or the same power with better precision, provided you manage losses, because every reflection, imperfect coating or scatterer mixes in ordinary vacuum that partially unsqueezes what you so carefully prepared. That sensitivity to loss is both a curse and an honest teacher. The amount of noise reduction you see in decibels shrinks linearly with total detection efficiency, so mode matching, clean optics, and high quantum efficiency detectors are not luxuries. They are the very currency that converts quantum advantage into a practical number. Calibration is the second pillar of honesty. Claiming below shot noise means defining shot noise rigorously for your exact setup. Block the signal path, keep optical power and bandwidth identical, measure the electronic noise floor separately and ensure it sits well below the optical noise. Then compare spectra in identical units, because it is too easy to beat a poorly defined baseline by accident. You also need phase control. Squeezing helps only if the ellipse is aligned with the signal quadrature, so you build feedback loops that lock the local oscillator's phase to the squeezed angle, using dither tones or pilot sidebands that tell the servo which way to nudge. In high-power interferometers, you must also prevent the squeezed field from feeding technical noise backward, so isolators and Faraday rotators enforce one-way travel, while filter cavities tens of meters long set the desired quadrature rotation without adding excess loss. Not all squeezing is single-mode. Twin beam or two-mode squeezing creates entangled intensity or phase correlations between two beams, and if your measurement compares two places or two colors, differential absorption across a sample, refractive index differences, scattered versus transmitted light. These correlations let common noise cancel while the quantum link preserves the signal, an approach that opens doors to correlated imaging and spectroscopy in which the reference channel needs almost no photons because its uncertainty is inherited from its twin. The limits are clear and practical. Squeezing does not save you from classical noise like laser excess intensity or thermal drifts, and it does not help if the signal itself couples mostly to the anti-squeeze quadrature. At very low frequencies, technical flicker and mechanical creep swamp quantum gains unless the entire apparatus is quieted. At very high frequencies, detector dark noise can hide improvements unless you use low noise electronics and keep optical power high enough that light noise dominates the baseline. There is also a philosophical boundary, heaping more squeezing onto a sensor without redesigning. The rest of the measurement rarely pushes you anywhere near absolute quantum limits because back action and inefficiencies rise to claim the budget, which is why the best gains come from co-design, choosing readout topology, mechanical susceptibility, and optical paths so that the squeezed resource is spent where it buys the most. Concrete recipes make all this less mystical. Begin with a sub-threshold parametric oscillator locked to a stable reference. Measure its noise spectrum with a shot noise calibrated homodyne detector to confirm genuine squeezing over your band of interest. Pass the squeezed field through mode cleaners to match the main interferometer. Inject at the detection port and watch the noise floor dip uniformly unless you purposely misalign the squeezing angle. Then add a filter cavity if radiation pressure matters, and iteratively improve losses. Better coatings, fewer surfaces, higher finesse cavities, while maintaining control of phase with slow and fast loops. Finally, validate not just by plotting a lower noise, but by showing a real signal to noise improvement on a calibrated tone or a known physical signal at constant power. The reward for this discipline is not abstract. More sensitive length readouts translate into earlier alerts for gravitational waves, lower optical doses for fragile samples, finer frequency resolution in spectroscopy, and improved phase tracking in coherent communications where you can beat classical shot noise limits without paying in extra photons. Carry one careful distinction. As you summarize the lesson, squeezing is not about violating uncertainty. It is about apportioning it, deciding which variable you care about, and sending the unavoidable randomness into its partner. And carry one practical mantra too. Quantum advantage is a systems property. Losses, phase noise, and calibration decide whether beautifully squeezed states on the bench become real gains at the sensor. So the craft is less about bragging rights in decibels and more about integrating a shaped vacuum into an instrument that asks the right question and listens along. The quiet axis you designed, zero noise extrapolation, and probabilistic error cancellation. Imagine asking a noisy quantum processor to tell you what an ideal one would have said, not by pretending the noise isn't there, but by using the noise against itself. First, by turning its strength into a dial you can sweep, and then reading off the zero noise answer by extrapolation. And second, by learning the processor's specific mistakes well enough that you can statistically anti-noise your data shot by shot. These two strategies, zero noise extrapolation and probabilistic error cancellation, are the backbone of error mitigation, a pragmatic middle path between doing nothing and the full grandeur of error correction. And if you understand what they assume, how to implement them, and where they break, you can extract honest physics from near-term devices that would otherwise blur delicate signals into averages. Begin with ZNE's intuition. If you can scale the noise in your circuit by a known factor while keeping the intended computation untouched, then the measured observable becomes a smooth function of that scale. So by sampling at several inflated noise points and fitting a curve back to where the scale is zero, you estimate what the ideal circuit would have produced. In practice, you don't have a knob labeled noise, so you synthesize one. On gate-based hardware, you can fold unitary layers or stretch pulse durations while compensating amplitude so that the logical operation is the same, but the time exposed to decoherence grows. On trapped ion or neutral atom platforms, you can lengthen entangling pulses, add idles with randomized compiling to keep the coherent content in check, or deliberately insert pairs of cancelling gates that add noise but no net logic. Then you run the circuit at scaling factors like 1x, 2x, and fit the expectation values with a model, often a simple polynomial, sometimes a constrained form that respects bounds, to project back to the 0 point. The method is powerful precisely because it is agnostic to microscopic error sources, but its honesty depends on a few non-negotiables. The noise must scale roughly smoothly over the range you probe. The noise should not change its character as you scale, and your added operations must be close enough to inverses that they don't inject systematic bias. You validate these assumptions with sanity checks. Shuffle the order of scale points to catch drift. Repeat the 1x run at the end to see if the baseline moved. Compare different folding patterns and test extrapolated outputs on circuits whose ideal answers you know. ZNE's trade-off is statistical. By inflating noise, you increase variance and reduce useful signal per shot, and the extrapolation multiplies uncertainty further. So you need more samples to achieve the same error bars. Yet for observables like local energies or small correlators, the shot overhead is often manageable and careful curve choice. Linear for very shallow noise, quadratic when you see gentle curvature, keeps bias small while avoiding overfitting. Peck takes a bolder step. Rather than infer the zero noise value by trending, it tries to reconstruct the ideal expectation exactly in expectation by sampling cleverly from an inverse noise recipe. The recipe starts with a noise model at the gate level, a map of how each native operation deviates from its ideal and expresses the inverse of that map as a quasi-probability mixture of physically implementable operations. Then, instead of running the ideal gate, You randomly choose one of those implementable surrogates according to the mixture's absolute weights. Record a sign and a weight for that choice, and multiply your measured outcome by that signed weight. Average many such weighted outcomes, and the expectation value, in theory, equals the ideal value with zero bias. The dragon you must face is variance, the product of those absolute weights, often called the sampling overhead or G factor, controls how noisy your estimator becomes, and it grows with gate count and with how non-invertible your noise is. To keep grung tolerable, you must tame coherent errors by randomizing compilations into stochastic Pauli channels, so the inverse stays local. Choose decomposition bases that minimize total weight, and refresh your noise model frequently so that cancellations hit the actual errors rather than their last week's shadows. Building the model is its own craft. Full process tomography is too expensive, so you lean on scalable methods, cycle benchmarking, gate-set tomography variants, interleaved randomized benchmarking to get a local, approximately Markovian description that captures the channels relevant to your gates. You also incorporate readout mitigation into the same formalism by inverting the measured confusion matrix of the detectors and folding its weights into the PC estimator, else detector bias will dominate your beautiful gate cancellation. PEC shines when the circuit is modest in depth and locality. And when you value unbiasedness above raw sample cost, for example, chemistry Hamiltonian expectation values at short depth, calibration grade validation of small algorithmic primitives, or metrology where systematic bias is unacceptable, but it can become impractical when G balloons, which is where Z&E's bias variance bargain may win. The two methods are not rivals so much as complementary tools on the same bench. You can first use randomized compiling to tame coherent errors, apply Z&E to reduce residual bias at low cost, and reserve PEC for the most sensitive subroutines, or even blend them by using PEC on a reduced active region of the circuit, while using Z&E to mop up global drift. Across platforms, the engineering is concrete and different. Superconducting qubits offer pulse stretching and gate folding with careful amplitude recalibration, but they punish you for phase noise and crosstalk. So you interleave frequent reference runs and track stability with spectator qubits. Trapped ions let you scale entangling times cleanly, yet slow drifts in motional mode frequencies can break the smooth noise premise, so you embed frequent mode scans and restrict scaling ranges. Neutral atoms bring Rydberg blockade errors that are highly state-dependent, so your inverse channel must condition on computational basis populations, or else your PEC weights misfire. Regardless of hardware, you guard against self-deception with a short checklist. Define and lock a shot noise baseline for your classical readout chain so that improved numbers aren't electronics. Report confidence intervals that include fitting and bootstrap resampling uncertainty, not just binomial error. Verify mitigation on holdout circuits where the ground truth is known. Show stability under small changes of scaling grid or decomposition basis. And quantify cost with the same honesty as gain by reporting the effective sample overhead per digit of accuracy. Conceptually, these methods teach a clear lesson about quantum experiments under constraint. You can trade unbiasedness for variance, PEC, or bias for lower variance, Z&E, and the right choice depends on what your downstream use tolerates. An algorithm that feeds into a variational loop may prefer stable low-variance estimates, even if slightly biased, while a benchmark of a physical constant demands vanishing bias, even if it takes more time. They also remind you that quantum advantage is a systems property. Mitigation only pays if compilation scrambles coherent errors, if calibration keeps noise stationary across the sweep, and if your observable is robust to the weighting schemes you apply. When you get the ecosystem right, the payoff is practical and immediate. Material models that converge at depths your device can sustain, sensors that estimate weak signals without being buried under hardware quirks, and algorithm prototypes whose failures reflect physics, not just electronics. Carry this closing sentence as a distillation you can defend under questions. Zero noise extrapolation infers the ideal answer by measuring at inflated noise and rolling back to zero. while probabilistic error cancellation reconstructs it by sampling from an inverse noise recipe. Both are real, testable ways to harvest trustworthy results from imperfect quantum chips, provided you measure your own assumptions, count the variance you create, and let calibration and validation be as central to your protocol as the mitigation itself. Quantum sensors for dark matter candidates. Picture trying to hear a visitor who rarely knocks, speaks in whispers across an ocean of noise, and may not be a person at all, but a field that fills space and makes itself known only by tugging gently on the instruments you build. This is the mindset behind quantum sensors for dark matter candidates, where you design devices so quiet and so well matched to specific signatures that even a feeble, non-gravitational trace becomes audible. Begin with the ultralight possibilities, axions, axion-like particles, and dark photons, which behave less like swarms of particles and more like classical waves with well-defined frequencies set by their mass, and learn the first rule of wave hunting. Tune a high Q resonator to the expected tone and listen long enough that the signal builds while noise averages down. In practice, that means a microwave cavity threaded by a strong static magnetic field for axions, where axions could convert into real photons, a lumped LC circuit coupled to a pickup coil for dark photons, where a hidden field drives currents at its own frequency, or a ferromagnet, whose uniform precession mode can be driven by axion-induced effective fields, with magnons converted to microwave photons and counted one by one. The quantum advantage is not a slogan here, but a list of concrete tricks. Replace a hot amplifier with a near-quantum limited Josephson parametric device. Use squeezed vacuum injection so that the quadrature you read has subshot noise. And deploy qubits or single photon counters as the first stage so that energy quanta in the relevant band are not lost to thermal fog. The art is to scan, because you do not know the frequency in advance. Motorize tuning rods in a cavity, or vary the inductance and capacitance in a circuit to walk through frequency space. Dwell at each step for a time set by coherence and noise budgets, and stitch together a coverage map with honest sensitivity. A parallel thread targets candidates that couple to spins and clocks rather than to photons. Atomic magnetometers and co-magnetometers search for tiny, oscillatory or transient fields by comparing two species whose responses differ, cancelling environmental drifts while preserving any exotic torque. Networks of optical or microwave clocks look for a global, rhythmic modulation of fundamental constants. If a scalar dark matter field makes the electron mass or fine structure constant wobble ever so slightly, two separated clocks will agree on the rhythm but not on local noise, and cross-correlation lifts the wiggle above the floor. Similarly, atom interferometers and torsion balances can hunt for domain walls or transients, topological defects sweeping through the solar system that would shift phases or forces in a time-stamped, correlated way across distant labs. In solids, ensembles of color centers or superconducting circuits can serve as sensitive field probes and transient glitch detectors. A passing object or wave would imprint a phase or cause a coordinated spike that you distinguish from local hiccups by comparing many sensors. Mechanical platforms add a complementary ear. Levitated microspheres and ultra-high Q membranes measure tiniest forces near DC to kilohertz, listening for stochastic kicks or narrowband drives that cannot be blamed on thermal motion when the refrigeration, vibration isolation and readout are good enough. To keep confidence high, every platform pairs clever hardware with equally disciplined analysis. Matched filtering extracts weak, narrowband tones whose coherence time is set by the virial velocity of the galactic halo, synthetic injections, tiny calibration signals added in software or hardware without the analyzer's knowledge, test whether the pipeline would flag a true discovery. Daily and annual modulations in both amplitude and frequency become discriminants because Earth's motion, Doppler shifts a real galactic wave, while most lab noises do not follow the same celestial clock. Null channels and reversals, detuning off resonance, flipping magnetization, swapping isotopes, rotating a device, turn ambiguous excesses into confirmed backgrounds, or strengthen a candidate. And blinding protocols prevent wishful thinking from drifting thresholds. The limits you must respect are as practical as they are deep. Loss in the readout chain dilutes squeezing benefits. Materials add parasitic modes that hide signals. Magnetic and vibration isolation never reach perfection, and the immense parameter space, masses spanning many orders of magnitude, couplings that might favor photons, spins, or nuclear moments, forces deliberate choices so effort accrues where discovery potential is real rather than fashionable. There are also honest physical ceilings. Quantum backaction and thermal photons set noise floors that cannot be wished away, so designs lean into quantum non-demolition readout, cryogenic operation, and multiplexed arrays that trade one heroic sensor for many good ones. Even a null result is useful when reported with care. By publishing calibrated exclusions with clear assumptions about halo models and coupling types, each group carves out regions that guide the next iteration and allow combination with astrophysical constraints from stars, supernova, and cosmology. The crossovers with other fields are fertile rather than accidental. Technology from gravitational wave interferometers, filter cavities, stabilizers, squeezed sources, migrates into dark photon searches. Qubit-based amplifiers born for computation become single microwave photon detectors for axion hunts. Spaceborne cold atom interferometers designed for fundamental physics double as wideband dark matter monitors, and clock networks erected for timekeeping morph into distributed observatories for ultralight waves, with data shared and reanalyzed under multiple hypotheses. Perhaps the most valuable mental shift is philosophical but practical. Stop treating dark matter as one monolithic target and start thinking in signatures. Narrow band tones that drift slowly, transient pulses that sweep coherently, forces that couple like magnetic fields but do not obey Maxwell's equations, global modulations that appear across sensors, continents apart, and then design quantum instruments that are purpose-built for those signatures, with system-level strategies that convert every decibel of squeezing, every Kelvin of cooling, and every hour of integration into credible sensitivity. If you carry one closing sentence out of this chapter, let it be this: quantum sensors expand the search for dark matter by matching exquisitely quiet, tunable instruments to specific, testable signatures, waves, kicks, and drifts, and when paired with disciplined scanning, controls, and cross-checks, they turn the near-impossible task of hearing the universe's quietest visitor into a problem of honest engineering and patient listening. Analog simulations of lattice gauge theories. Tilt your perspective for a moment and imagine building a tiny universe on a tabletop, not by drawing equations on a board, but by arranging atoms, ions, or superconducting circuits so that their allowed moves are the very laws of a gauge theory. Charges living on sites, fields living on links, and an inviolable local rule, Gauss's law, that decides which configurations even exist. That is the ambition of analog simulations of lattice gauge theories, where you don't numerically approximate the dynamics of electric and magnetic fields. You let matter waves and engineered couplings become those fields, and time itself becomes your solver. To ground this in something you can picture, recall that a lattice gauge theory assigns matter to vertices and gauge fields to the bonds between them, then penalizes any local violation of charge conservation so strongly that only physical states survive. And the Hamiltonian you write, kinetic matter terms, electric field energy, and plaquette ring exchange that mimics magnetic flux, maps naturally to platforms whose interactions you can sculpt. In optical lattices, hopping fermions play the role of matter while bosons, or spin degrees of freedom, on the links encode electric flux as occupation or spin orientation. In trapped ions, internal states of each ion can serve as link variables, while phonon-mediated couplings create the plaquette terms. In superconducting circuits, microwave photons in resonators become electric fields, and tunable couplers implement four-body ring exchanges. Even in arrays of polar molecules or Rydberg ensembles, blockade and dipolar processes can enforce the local constraints that are the beating heart of a gauge symmetry, the trick that turns nice metaphor into honest simulation is gauge, protection, designing the system so states that break. Gauss's law are energetically out of reach or dynamically suppressed, achieved by large detunings that punish wrong charge flux combinations, by engineered interactions whose minima occur exactly at divergence-free configurations, or by symmetrized couplings that make forbidden moves destructively interfere. Once that scaffold is firm, you can stage textbook phenomena in real time. Prepare a particle-antiparticle pair in a one-dimensional U1 model, the lattice Schwinger model, and watch the electric flux stretch into a string between them. Raise the field's energy cost and the string refuses to break. A visual lesson in confinement. Lower it past a threshold and the string snaps by, spontaneously creating new pairs that screen the field. A dynamic picture of string breaking. Quench the staggering that mimics a mass term, and you witness false vacuum decay as the system tunnels and then avalanches into a lower energy sector, leaving behind domains and oscillations you can film with site-resolved microscopes. Step to higher dimensions, and ring exchange around a plaquette plays the role of magnetic energy. By dialing the strength of the four-body process, you can tip the balance between confined phases, where Wilson loops obey an area law, and fields are trapped into narrow tubes, and deconfined phases where perimeter laws announce free flux lines. In Z2 and Zn models, spins on links, simple, discrete surrogates for continuous gauge fields, capture much of the same physics with fewer resources, letting you test how defects move, bind, or condense when you nudge parameters, and how emergent visons or enyon-like excitations show up in interference patterns and quenches. None of this requires blind faith. The observables are concrete and local. Measure electric flux on each link via occupation or spin readout. Reconstruct gauge invariant strings by multiplying link variables along a path, and extract Wilson loops from products around a closed contour. Monitor Gauss's law at each site as a health meter and watch violations stay near baseline if your protection works. Track entanglement growth after a quench to see how information spreads differently in confined versus deconfined regimes, or measure string tension directly by moving charges apart with optical tweezers or programmable gates and reading back the work stored in the field. Design knobs are equally tangible. A staggered potential acts like a tunable Fermion mass. A background field appears as a bias that prefers one flux orientation. Boundary conditions are set by closing a ring of sites or by engineering reflective edges that return flux. And plaquette strength is a dial you realize with ring exchange pathways tuned by laser-assisted tunneling, parametric couplings, or multi-qubit drives that synthesize the needed four-operator product. Challenges are real and instructive, not fatal. Unwanted long-range couplings can leak probability into symmetry-violating sectors, so you shape interactions with band gaps, detuning hierarchies, and cancellation sequences that average away off-target terms. Disorder and inhomogeneities tilt the energy landscape, so you pre-compensate with site-resolved offsets and calibrate against the Gauss law histogram. Heating and decoherence limit observation time, which you extend by working in regimes where the interesting dynamics occur early, by cooling vibrational modes that mediate couplings, and by reading out with minimal back-action. Even the thorny issue of mapping continuous groups U1, SU2 onto finite resources is handled cleanly with quantum link models. Replace an infinite dimensional field on each link with a finite spin representation whose low-energy sector still hosts the desired physics. String tension, confinement transitions, even rudiments of non-abelian dynamics like color electric fluxes that can change orientation while keeping the simulator manageable. What makes analog simulation more than a curiosity is its reach into regimes that challenge classical computation. Real-time dynamics after strong quenches, far from equilibrium string fragmentation, and entanglement structures in two spatial dimensions where Monte Carlo methods stumble on sign problems. By coupling matter and gauge fields natively, these platforms expose how charges drag fields and how fields back-react on charges in a way that effective spin models cannot fake, letting you test whether intuitive pictures, like domain wall melting as a proxy for string breaking, survive when the full gauge constraint is active. Verification remains the arbiter of trust, so disciplined groups interleave easy circuits whose outcomes are known. Short loops, small plaquettes, integrable limits, with ambitious runs, benchmark their Gauss law stability over time, and use tomography only where local structure matters, leaning instead on gauge invariant correlators that scale to larger systems. They also perform falsification tests, intentionally weaken gauge protection and show that confinement signatures collapse, change boundary conditions, and demonstrate that Wilson loops respond as theory predicts, scramble link matter couplings and watch the disappearance of string tension. Taken together, these checks convert pretty movies into credible physics. Conceptually, the payoff is twofold. You gain a tactile grasp of abstract ideas, fields as constraints, forces as geometry, charges as sources, and you acquire a laboratory for exploring universality by deforming details and watching invariant features persist. Practically, the same hardware innovations that make gauge simulators possible. Site-resolved control, multi-body interactions, protected subspaces, spill into quantum technologies for error suppression and robust encoding. Perhaps the lasting reflection to carry out of this chapter is that simulating here does not mean pretending. It means building a machine whose native language is the symmetry you care about, and then asking questions in that language. When you think this way, a cold atom microscope, an ion chain, or a chip of resonators becomes less a calculator and more a curated microcosm. Charges breathe, fields stretch, strings break or hold, and by watching those acts under conditions no supercomputer can comfortably follow, you learn not only what a particular model does, but how local rules, enforced strictly and read out honestly, give rise to the collective orders that shape the physics of our larger world. Continuous variable, quantum computing. Imagine doing quantum computing not by flipping tiny coins that are only ever heads or tails, but by sculpting ripples on a continuous pond. Each ripple carrying a phase and an amplitude you can tune with exquisite finesse, so that information lives in smooth variables rather than in rigid bits. That is the promise of continuous variable quantum computing, where the basic carriers are bosonic modes, light in an optical fiber, microwaves in a resonator, vibrations in a mechanical element, and the registers are their quadratures, two complementary degrees of freedom that behave like the real and imaginary parts of a wave and can be displaced, rotated, and squeezed to form the raw material for computation. You begin with Gaussian states because they are the easiest to make and control. Vacuum, coherent states, and squeezed states whose noise ellipse is narrowed along one quadrature and widened along the other, all stitched together by Gaussian operations such as phase shifters, beam splitters, squeezers, and linear interferometers. With only those tools you already gain a remarkable superpower, deterministic entanglement at scale, by interfering many squeezed modes to weave cluster states, giant webs of correlations that measurement-based computing can consume one homodyne readout at a time, while adaptive feed-forward steers the computation through the graph. In this picture, gates are choices of measurement bases and classical updates, and universality comes within reach if you add just one ingredient that Gaussian optics cannot supply by itself: a genuinely non-Gaussian resource, the spark that bends the otherwise linear world into a fully programmable computer. The non-Gaussian doorway can be opened in several honest ways. Prepare a cubic-like ancillary state that imprints curved phase on a target via teleportation. Enact a weak Kerr interaction that distorts the Wigner function beyond an ellipse, or perform photon addition and subtraction on squeezed light to carve states with ripples and negativity that Gaussian noise cannot mimic. Without that step, a purely Gaussian machine, even with mountains of squeezing, remains simulable by classical algorithms and cannot win the hardest fights. Once you accept the need for that spark, a toolkit crystallizes. Heralded photon subtraction, using a beam splitter and a click, turns an otherwise benign squeezed state into a resource with teeth. Quantum non-demolition couplings, realized with ancillary modes and feed-forward, enact conditional displacements that build up effective nonlinearities, and temporal multiplexing, streaming a single squeezed source through interferometers that change in time, lets you knit cluster states with thousands of modes using compact hardware rather than a city of crystals. Measurement becomes your paintbrush. Balanced homodyne detection reads a chosen quadrature with shot noise-limited precision, while photon number resolving detectors enable the non-Gaussian projections that upgrade the gate set. To keep your footing, it helps to frame the landscape in resource language. Gaussian operations are free. Squeezing is a currency you must spend wisely, and Wigner negativity is the cost of doing anything truly quantum advantaged. From here, the real engineering begins, because loss and phase noise are both relentless and particular. Loss drags states toward vacuum and erases the very negativity you work to create, while phase drift washes target axes so that intended gates smear across the plane. You fight back by boosting detection efficiency to keep every photon you can, locking local oscillators so that measurement bases stay where you left them, and embedding error-correcting structure at the physical level so noise does not accumulate unchecked. This is where bosonic encodings shine. Instead of guarding a logical qubit with many physical qubits, you hide it inside one mode's infinite ladder of states in a way that pairs natural errors with simple, frequent fixes. Cat codes store information in superpositions of coherent states whose even-odd parity can be checked non-destructively, letting you correct single photon loss by restoring symmetry. Binomial codes tailor exact photon number superpositions so that common errors map to orthogonal subspaces you can diagnose, and GKP codes inscribe a grid in phase space, a comb of narrow peaks that repeat regularly, so that small shifts in amplitude or phase can be sensed as displacements and pushed back toward the nearest lattice point. Because homodyne detection already measures displacements with high precision, GKP stabilizers fit continuous variable hardware like a glove, turning an analog sensor into a digital guardian. Meanwhile, measurement-based computing dovetails with these codes by letting you teleport through small error-correcting gadgets sprinkled along the cluster, so that logical noise is shaved off as you go. Platforms diversify the story without changing its grammar. In optics, room temperature experiments generate tens of decibels of squeezing and knit kilometer-long temporal cluster states inside a shoebox of fiber, promising bandwidth and low decoherence, but demanding exquisite mode matching and a credible source of non-Gaussianity to close the gap to universality. In superconducting circuits, microwave resonators host CAT and GKP states that you can stabilize autonomously with tailored dissipation, and Josephson hardware provides the nonlinearities to create and measure the right patterns, all while operating in fridges where thermal photons are tame. In hybrid devices, mechanics couples to light so that a single nonlinearity can seed non-Gaussian structure across both optical and microwave domains, hinting at transduction-friendly processors. When you ask what CV computing is good for, the first answers are both practical and near-term. Simulation of systems whose Hamiltonians are naturally quadratic, plus a sprinkle of nonlinearity. Gaussian boson sampling and its variants, which leverage large interferometers and squeezed inputs to produce distributions hard for classical machines to emulate. Quantum machine learning primitives that operate on continuous data, where kernel methods and Gaussian processes find native quantum footprints, and precision sensing pipelines in which a CV processor prepares, routes, and reads states optimized for a metrological task before any sampling overhead overwhelms you. Honesty, though, insists on the fault tolerance ledger. Thresholds depend on how much squeezing you can muster, how often and how well you can perform non-Gaussian operations, and how low your loss is over the entire circuit. Very high squeezing buys you code distance, but makes your resource states fragile. Frequent non-Gaussian kicks keep universality alive, but cost rate and complexity. And loss threatens to dissolve both entanglement and negativity, unless you fold error correction into the very bones of the architecture. This is why the field gravitates toward co-design, choosing codings, often GKP, that speak the hardware's native language, build cluster states whose graph supports inline correction, and reserve scarce non-Gaussian steps for places where they maximize logical progress per photon. Verification keeps ambitions grounded. Gaussian processes are fully characterized by means and covariances, so you benchmark the linear skeleton with tomography that scales well, and then isolate non-Gaussian elements with targeted witnesses. Negativity of the reconstructed Wigner slice, photon number statistics inconsistent with any ellipse. Gate teleportation that reproduces curved phase maps within error bars. You also report end-to-end logical metrics, not just state-level prettiness. How many logical operations per second at what logical error rate, under which loss and phase budget? If these sound like constraints rather than romance, that is the maturity of the field talking. CV hardware trades the scarcity of high-quality two-level systems for abundance of modes and deterministic entanglement, and then pays honestly for the scarce ingredient, non-Gaussianity, by engineering steps that are heralded, efficient, and compatible with codes. The conceptual reward is a reframing of what quantum digits can be. Information need not sit in discrete clicks to be powerful. It can ride on continuous waves if you learn to discretize the corrections rather than the carriers, to linearize the plumbing and localize the nonlinearity, and to let measurement and feed forward be first-class citizens rather than afterthoughts. As you leave this chapter, keep one compact truth you can defend. Continuous variable quantum computing turns modes into registers and quadratures into levers, gives you universal power when a single non-Gaussian spark joins a sea of Gaussian ease, and becomes practical when bosonic codes and high-efficiency readout convert an analog world into a digitally protected one, an approach that favors scale and throughput while demanding discipline about loss, phase, and the careful spending of every photon of nonlinearity, topological magnonics, and protected transport. Consider sending ripples through a magnet the way you might watch wind push patterns across tall grass. Not charges moving down a wire, but collective twists of countless spins marching together. And then imagine shaping the landscape so that some ripples must circle the boundary in a single direction, refusing to backscatter no matter how rough the edge becomes. This is the invitation of topological magnonics and its promise of protected transport, where the information carrier is the magnon, a quantum of a spin wave in an insulating magnet, and the highway is not a metal trace, but a band structure engineered to host chiral edge channels that keep going. Even when disorder and bends try to turn them around, start gently with what a magnon is in practice. Take a ferromagnetic film, such as yttrium iron garnet, align its spins with a modest magnetic field, and nudge them with microwaves or a local heater so they precess slightly out of step. That synchronized wobble propagates as a wave, carrying angular momentum without moving electrical charge, which means almost no Joule heating and a natural compatibility with dielectrics. Now layer on geometry and interaction. When the magnetic lattice lacks inversion symmetry, or when interfaces supply a particular chiral twist through spin-orbit effects, the dispersion of those waves picks up an internal handedness encoded in Berry curvature, a geometric quantity that behaves like a magnetic field in momentum space. When this curvature integrates to a non-zero integer across a band, you have a topologically non-trivial magnum band and, by the same reasoning that protects electronic quantum Hall edges, you acquire one-way magnum channels pinned to the boundary whose direction is set by the overall magnetization. These channels are not slogans, but experimentally visible features. Drive a microwave antenna near one edge, and the signal races along that edge in a preferred direction, skimming around defects and not returning to the source, while the opposite edge carries the counter-propagating partner. Heat a corner and a transverse temperature-driven flow develops. The magnonic thermal Hall effect, signaling that geometry, not just scattering, is moving energy sideways. To build such bands pragmatically, you can pattern a magnonic crystal by perforating a film into a honeycomb or Kagome network so that the spin wave sees a periodic potential with Dirac-like crossings that you then gap with chiral interactions. Or you can rely on intrinsic chiral couplings, Dzialoszynski-Moria interactions at heavy metal interfaces or in non-centrosymmetric magnets that twist spin textures and imprint curvature without lithography. Dipolar interactions at long wavelengths add another, more classical route. They break time reversal symmetry for certain modes and lift degeneracies so that even simple stripes can host non-reciprocal surface waves, though truly robust edge channels benefit from lattice-scale chirality that yields well-isolated bands. Your immediate payoff for all this structure is transport that laughs at moderate roughness. Edge magnons do not have a backward state at the same energy to scatter into, so small voids, thickness fluctuations, and modest corners cause phase slips rather than reflection. You can bend a waveguide around tight radii, route it across junctions, and still recover the signal downstream, a property that microwave engineers exploit to make circulators, isolators, and delay lines that operate with vanishing on-chip power. Because magnons live at gigahertz to terahertz frequencies depending on field and material, the same platform can talk to both classical RF circuits and quantum hardware. Place a magnetic film inside a microwave cavity, and the hybridized modes, magnon-photon polaritons, inherit some immunity from the magnon's topology while offering clean readout. Couple those modes to superconducting qubits, and you sketch a future in which quantum states are transduced to sturdy, topologically guided spin waves that shuttle information across a cryostat without lossy coax. The story deepens when you add temperature gradients and spin currents. In spin caloritronics, a heat flow generates a magnon flow that can be harvested electrically through the inverse spin Hall effect in an adjacent metal. Engineer that flow into edge channels and you gain thermal logic elements where heat drives one-way signals, potentially turning waste power into useful control. Equally, electrical current in a heavy metal injects angular momentum into the magnet through spin-orbit torques, letting you steer edge channel population with DC currents rather than only with fields or microwaves. Honesty insists we map the limits, and they are practical, not mystical. Magnetic damping eats magnons over distances set by materials science. So protected does not mean lossless. Topology suppresses backscattering but does not cancel friction. Mode crowding can mix edge and bulk bands if the patterned lattice is not precise. So clean gaps and careful thickness control matter. Thermal Hall signatures can arise from ordinary skew scattering if disorder is strong. So you must distinguish geometric contributions by mapping how signals scale with field direction, thickness, and edge orientation, and the very interactions that endow chirality. Interfacial spin-orbit coupling, chiral exchange, can introduce inhomogeneity and extra loss if deposited carelessly. The engineering countermeasures are specific and teachable. Use low-damping garnets or hexaferrites for long propagation lengths. Pattern with electron beam or focused ion beam steps that respect crystal integrity, and cap with clean heavy metals whose spin transparency is known. Extract band geometry indirectly but reliably by matching measured dispersion to models. By using Brillouin light scattering to map mode profiles along edges and in the bulk, and by tracking non-reciprocal antenna-to-antenna transmission as you reverse magnetization. Reconfigurability is a quiet superpower here. By locally reversing magnetization with a microcoil, or by toggling gate-controlled interfacial currents that adjust effective chirality, you can rewire the edge network in real time, opening and closing paths or launching domain walls that act as movable waveguides for spin waves. Domain walls themselves add nuance. They can host their own bound magnon modes that march along the wall like trains on a temporary track. And because walls are programmable with field or current, they offer an alternative to lithographic edges, a soft, rewritable circuitry where the wires are magnetic textures you draw and erase. Interactions take you beyond single particle transport into nonlinear territory that is as rich as it is useful. Parametric pumping can amplify selected modes without touching others. 3. Magnon and four-magnon processes redistribute energy in ways that sometimes heal defects and sometimes saturate signals. And weak nonlinearity in a topological band can support robust, soliton-like packets that keep shape over long distances. With such tools, you can imagine logic that uses amplitude and phase in analog fashion, routing, gating, and mixing signals with almost no current flow. And you can picture neuromorphic elements, where spin-wave interference implements weighted sums, while topology keeps the pathways from unintentional crosstalk. Integration with CMOS is more than a footnote. Because the magnets are insulating, you can place them above metallic interconnects without shorting. And you can read and write magnons electrically via small spin-orbit blocks at the edges, turning topological channels into drop-in links that relieve thermal budgets on crowded chips. The deepest intellectual gift of this field is the way it redefines robustness for waves that are not electrons. You learn to think of protection as a property of a band's geometry, how its phases wind as momentum loops the zone, rather than as a detail of a device's sidewall. You also learn that topology does not make dissipation vanish. It makes scattering impotent, a more modest but more honest promise that holds up in the lab. And you discover that magnets bring their own charms to the topological table, tunable by field, current, or temperature, compatible with room temperature operation in many materials, interfaceable with optics through magneto-optical effects, and with mechanics via magneto-elastic coupling, which suggests hybrid chips where photons write, magnons carry, and phonons store. If you need a practical checklist before you build, keep it spare and direct. Pick a low-damping film and confirm its dispersion. Pattern a lattice that supports a well-gapped edge band and verify it with light scattering or near-field microwave probes. Add heavy metal contacts for electrical control and spin-to-charge conversion. Test non-reciprocity by flipping magnetization and measuring edge-to-edge transmission. And map thermal and magnetic noise so you can quote propagation lengths that survive real environments. Then let ambition grow. Cascade 2 edge devices into a ring to make an interference gyroscope for magnons. Couple an edge to a cavity to explore chiral strong coupling. Stitch domains to reconfigure pathways dynamically. And keep materials work close at hand, because every decibel of lower damping turns protected into practical. As you close this chapter, hold one sentence you can share without overclaiming. Topological magnonics turns spin waves in insulating magnets into one-way edge currents, whose immunity to backscattering enables low-power, reconfigurable transport, not a miracle cure for loss, but a geometric safeguard that, when paired with good materials and careful design, lets information glide where electrons would overheat and where ordinary waves would turn back, when particle is the wrong word entirely. What if the thing you've been calling a particle is only a convenient story for when the world is quiet, and the moment you turn up the interactions, bend the geometry, or cool matter into collective order, the story unravels and you have to speak a different language altogether? Start here. A particle is supposed to be a tiny, countable traveler with a path you could at least imagine. Yet in many of the most revealing regimes of modern physics, what moves is not a speck but a pattern, an organized ripple of many constituents, a seam in an ordered fabric, a knot in a field, and the only honest way to track it is to follow the pattern, not the supposed thing. In a one-dimensional wire, for instance, electrons do not keep their identities long enough to deserve name tags. Every attempt to push one immediately stirs the entire line into a coordinated shiver known as a Luttinger liquid, where charge and spin separate and neither behaves like a solitary traveler. In certain two-dimensional magnets, you can pull on a single spin and watch the disturbance split into pieces that carry fractions of the original quantum numbers, anyone's whose exchange is not the polite swap of billiard balls but a twist that imprints a memory on the whole wave function, so counting them like beads misses the point, because the identity lives in the choreography, not the bead. Even metals, the paradigms of single particle motion, betray this picture when pushed to extremes. Some high-temperature superconductors and strange metals refuse to be explained by long-lived electron-like excitations at all, conducting instead through a soup whose behavior is better summarized by universal relaxation rates and hydrodynamic flow than by trajectories. In very clean materials at the right temperatures, ordinary electrons stop scattering primarily off impurities and start scattering mostly off each other, and current flows like honey rather than as a parade of independent charges. Narrow channels develop whirlpools and viscous profiles that make more sense in the language of fluids than in a cartoon of particles passing through a turnstile. Venture into topologically ordered phases, quantum, Hall fluids and spin liquids, and you find ground states woven with long-range entanglement, where no local probe can assign properties to a single object without referencing a global constraint. Excitations behave like endpoints of invisible strings, and moving one endpoint around another changes the state in a way no local measurement can fully capture. Push further into fractal matter, and mobility itself becomes a property you cannot give to an isolated particle. Defects are pinned by the very rules of the phase and can move only as bound clusters along specific directions. So the currency of dynamics is not a thing traveling, but a rulebook of allowed rearrangements etched into the many-body pattern. Even in the quantum vacuum, the word particle needs context. Accelerate your detector and you will swear the void is warm, a reminder that what counts as a particle depends on the motion of the observer and on which field modes they choose to call quiet. Close to absolute zero in superfluid helium, the simplest excitations are phonons and rotons, collective swells and folds in the liquid. And when heat flows, it does so by the drift of these patterns, not the march of microscopic atoms treated as independent carriers. In photonics and plasmonics, the same lesson repeats with a new wardrobe. What engineers root are hybrid waves, light married to matter into polaritons, surface plasmons glued to metal boundaries, topological edge modes that owe their resilience to geometry rather than to individual photons soldiering on. And losses, gains and phase are the verbs you must speak. In early universe and heavy ion physics, the notion of a sharp quasi-particle collapses into a strongly coupled fluid whose gradients and symmetries tell more truth than any imagined gas of weakly interacting constituents. Even the mathematics you use signals the shift. When response functions are smooth and long-lived poles dominate, the particle picture works. When spectra broaden and memory effects matter, the poles sink into a continuum and the faithful description turns into hydrodynamics, kinetics, or effective gauge fields that track constraints, not corpuscles. This is not license to abandon intuition, but a nudge to update it. Ask first what is conserved and on what timescale. Momentum, vorticity, topology, entanglement patterns, and let those answers pick the language. If the system's hallmark is a global constraint, learn to draw strings, loops, and fluxes. If relaxation is fast but local conservation survives, write the hydrodynamic equations and forget about counting. If braiding leaves indelible phases, speak anyone's and topology rather than particles and collisions, and be humble about measurement, because what you see often depends on the tool you use. Angle-resolved photoemission might insist there are no sharp electron-like lines in a strange metal, while thermal transport quietly follows a viscosity law. A microwave resonator measures a collective mode's life, not an electron step count. A scanning probe maps a standing wave of spins that exists only as a chorus. When you design devices around these truths, power follows clarity. You build interconnects that move spin or heat with minimal loss by shaping band geometry, not by pleading with electrons to behave. You store information in non-local patterns that errors cannot nibble away locally rather than in fragile local bits. You probe biological and nanoscale systems with sensors that read fields and flows, not particles and paths, because the energy budget and the relevant physics live in the continuum. The ethical claim of this chapter is modest and testable. The word particle is a tool, not a creed, and the world will tell you when to lay it down if you listen for broadened lines. Missing quasi-particle peaks, non-local responses, protected edge currents, restricted mobility, or fluid-like transport. The reward for that flexibility is a larger, kinder map of phenomena where seemingly disparate effects, fractional statistics in a two-dimensional electron sea, viscosity in a micron-wide channel, mobility rules in a fracton crystal, braiding phases that store quantum information, sit under one umbrella, patterns and constraints as first citizens. Take this with you when you meet the next surprising experiment. Before you call the culprit a particle, ask whether you are actually watching a wave stitched from many bodies, a defect in an order parameter, a slice of topology, or a field obeying a conservation law on a time you had not considered. Let the system teach you its nouns, and end with a quiet conviction that simplifies rather than mystifies. Reality is generous with stories, but the true ones are the ones whose nouns match the verbs on the stage. In many of the most interesting theatres we have built and found, the verbs are interference, flow, braid, and constrain, and the right noun is not particle, but pattern, which once seen is impossible to unsee.